Hello everyone, welcome to the Samsung AI Forum 2020. My name is Kyungmi Kim and I'll be hosting today's program. Due to the COVID-19, Samsung AI Forum 2020 will proceed via online live streaming. Many people have joined us online both yesterday and today, and I thank all of you for your precious time. In today's Samsung AI Forum 2020 Day 2, hosted by Samsung Research, with the topic of human-centered AI, we'll discuss how AI, by understanding and communicating with humans, can make the world a better place. In today's forum, we'll be accepting questions real-time during the session presentations. Among them, we'll select several questions and hear from the panelists during Q&A sessions and panel discussions. So we await your participation. So let us begin with the Samsung AI Forum 2020 Day 2. For today's forum, we have invited actively researching AI experts from around the globe. So please look forward to it. First and foremost, we have an opening keynote from Sebastian Sung, Corporate President of Samsung Electronics.
Hello everyone, and welcome to the Samsung AI Forum 2020. My name is Sebastian Sung, and I'm the president of Samsung Research. We're hosting today's session about AI. Because of coronavirus, this conference is being held online, but we want it to be as interactive as possible. So you've all received an email about how to submit your questions online. These questions might be about particular talks that you hear, or they might be general in nature to be addressed to the speakers in the panel discussion that will conclude today's session. I'm really excited to say that we have some incredible speakers ahead, but I'd like to start off this day by describing a little bit about Samsung's research in AI. The title of today's session is Human-Centered AI because, after all, that's what we at Samsung are interested in. We want to have technology that actually benefits people. And to that end, we've built up AI research in traditional AI areas like vision and graphics, speech and language, robotics. We also have a big effort in on-device AI. How can we make our AI run on devices that had limited computational power, limited consumption of electrical power, and so on? And I'll talk about an area which is not AI per se, which is health and wellness, a very fascinating area where we can benefit people by harnessing the power of AI and data and devices. The big picture goals of this talk. I'm not going to tell you about AI research per se. I'll leave that to my speakers. I want to give you a big picture. I want to show you the big picture within which AI research exists. And to do that, I'm going to show you specific examples of real-world applications of AI at Samsung. And we'll use those as a starting point to understand the big technological challenges that Samsung and AI researchers around the world are facing as we want to make AI's power extend as much as possible and help people as much as possible. Now, a few words about research in a company. I've done research at universities, I've worked at companies, and research in a university is all about freedom. You study what you want, you have fun, you study it because it's beautiful. But research in companies is very much about constraints. We have to solve real-world problems, and that might feel confining, but it also can be, strangely enough, a source of liberation. And we have here a famous quote from Orson Welles, who some people say is the greatest movie director of all time, here shown as a boy genius. He once said that the enemy of art is the absence of limitations. And the story goes, he was explaining how one day he had to make a movie and he had a limited budget. He didn't have enough dollars. But he realized that that limitation forced him to be more creative and more innovative. By solving these problems inside a limited budget, he was able to make a greater masterpiece. And in the best of worlds, that's what corporate research is like. Real-world constraints can stimulate our creative powers. So let's start with vision and graphics, a classic area of AI. And here we actually have a Samsung product pictured, which is a TV. So you may know, if you've gone to buy a TV, that TVs are crazy these days. 8K TVs, they're huge. They have incredible resolution. Real progress in the hardware since HD and 4K, now we have this 8K. But the funny thing is, those 8K TVs often look useless, because if you're viewing content that was made in HD, it still looks like an HD TV. You actually have to have high resolution 8K content to fully show off the immersive experience of that TV. What are you going to do? AI to the rescue. Maybe we can make a convolutional net that takes HD content as input and spits out something that looks like 8K content. A simulation of 8K imagined by the convolutional net. Now, you may know that convolutional nets are tailor-made for this kind of thing. Multi-scale architectures. These are able to produce, and also training with GANs and so on and so forth, these are able to produce extremely realistic upscaled images. And on the right you see an AI upscaler, on the left you see one from a conventional image processing approach. And so that's the kind of approach. Build inside your TV a little AI that can automatically turn HD content into 8K content. Now, that kind of sounds a little bit easy because we know as academics that that sort of thing is possible. It turns out it's not that easy to get it to run on the limited processing power of the TV, and I'll get to that later. That's something very non-trivial. Now, just getting to a little bit more far out application, not a current product, let's think about telepresence. We spend our lives on Zoom these days. And so obviously it's important to think about technologies that could enhance the Zoom experience. One of them is the neural avatar. And this is from a paper that was put out by the Moscow AI Center, Viktor Lempitsky's group at Samsung Research. They got a lot of attention on Twitter last year because of this. It's a so-called deep fake, right? So from one photo, the neural net can be used to synthesize a talking head, just from one photo. From 8 photos, of course, even better. And here's the trick, not just with a real person, but with the Mona Lisa talking head. And of course, I guess our researchers couldn't resist making the Sebastian Sung talking head. And so you've heard about deepfakes. Many people are afraid of deepfakes because they could lead to bad behaviors, misleading things available on the internet. But of course, neural avatars are the good word for that, and neural avatars could be very useful for telepresence or augmented reality. And they're just a really cool application of AI. All right, so let's move on to on-device AI. As I told you before, making an AI upscaler run on a TV is a big challenge because of the limited computational resources, right? If I have a convolutional net and I want it to run on a supercomputer somewhere in the cloud, that's one thing. But if I want it to run on the limited processor of your TV, if I want it to run on your phone and not exhaust your battery immediately, or run on a robot, then we have to make a neural net that can run on device. The other bonuses of on device would be fast response time, right? No network latency. You don't have to go, the robot doesn't have to communicate with some faraway computer. It has its processing inside itself. And possibly on-device AI might be helpful for protecting consumer privacy. It's not a full solution, but leaving data on the device could be, instead of sucking it up into the cloud, could be helpful for protecting consumer privacy. So all these are bonuses of on-device AI. And you might want to dismiss on-device AI as, that's just some engineering. But in fact, I would say it's fundamental. Also, the brain. The human brain is extremely efficient in its operation. One human brain operates on 1/4 the power budget of a light bulb, a tiny amount of power. And if you compare, say, to the supercomputer that defeated Lee Sedol in Go, many orders of magnitude difference in power consumption. And the brain has evolved to be energy efficient. That's just the pressure over the millions and billions of years of evolution that our brains have become extremely energy efficient. Not just human brains, fly brains. Imagine that a fly's brain has a lot of visual processing power and uses even less energy and takes up less space than a human brain. Now, in neural nets, efficiency means fewer connections. If you make a neural net with fewer connections, it's going to be more efficient, both in computational time, in memory consumption, and so on. And going even further, if those connections have fewer bits in them, right? You could imagine that one connection in a neural net is 16 bits, or you could imagine only 1 bit maybe, off or on. So the number of bits, the analog precision required to store a connection in a neural net is a big determiner of how efficient it is. And so there's a lot of interesting work going on in so-called model compression, trying to make neural nets with fewer connections and fewer bits per connection. And I'm very proud of recent work from Samsung Research, led by Dong-Soo Lee. This is one paper of theirs accepted at NeurIPS, but they also have other really fantastic papers this year on neural nets with fractional bits per connection. So really huge compression ratio, very interesting advance. And so on-device AI, if you think about it, it's a very interesting thing, because on the one hand, you can imagine that AI will be inside the brains of our robots. You could also imagine that as our communication networks become more and more powerful, lower latency, higher bandwidth because of 5G and 6G innovations, you could imagine that robot would become stupider and stupider, that its intelligence would be in some faraway powerful computer. That's the idea of network intelligence, that all the intelligence will reside in the network, but not the devices. I think the reality is that there's going to be a split. Some AI will be in the robot or device, and some AI will be delivered through the network. And how that split will be made is a very interesting question for the future. So to what extent will AI be on device? Will it be running on a computer inside a robot? And to what extent will AI be delivered through the network? You could imagine that the robot itself would be dumb. It just receives its commands by communicating with some AI that's in the cloud somewhere. And that's going to become ever more possible because of 5G and 6G communication networks. The speed of communication, the bandwidth of communication between devices and centralized computers will keep on going up. So we're going to see network intelligence as well as on-device AI. And how will that split happen? It's a very interesting kind of question with a lot of implications for the future of technology. Moving on to speech and language. Speech and language are clearly important to Samsung and to many other companies that deliver computer-human interaction experiences. So here's a video from our marketing department, right? Samsung would like you to be able to talk to your smart home.
여기 일로 오세요. 야, 여기 있어. 나 갔다 올게. 하이 빅스비. 외출 모드 실행해줘.
네, 우리 집에서 외출 모드를 시작합니다.
So you see, this is paradise. I'm living at home. I'm surrounded by Samsung devices. The home is smart. And it understands when I tell it I'm leaving, and it knows what to do, right? But that paradise will not be realized unless the home has an AI that understands our instructions. And so speech and language are very important to Samsung and to many other kinds of tech companies. And we have, because of this, we have research in natural language understanding and speech recognition. We're very proud of this collaboration with Chris Manning's group at Stanford. Chris is going to be speaking later on in the session, but question answering is a really interesting challenge. You ask a question and the computer needs to answer you. A lot of activity on that in natural language processing, and we're participating in the open challenge Hot Pot QA, and we're doing very well. Now, I look at all this progress in natural language processing, and I think in the end, though, we would like to have not only question answering, but we want to see multi-turn dialogue between humans and computers. You want to be able to talk with a computer in a normal way, with a conversation that goes on for a while and actually comes to the root of a problem that you're having. We have a Samsung chatbot which provides customer support, and it is able to do some interaction with the customer, but only if we constrain the domain, right? And so the challenge here is, can we build true multi-turn dialogue systems that feel natural, feel satisfying, and yet we don't have to impose all these constraints? This is the big challenge for natural language understanding. Robotics. Robotics is really, personally, a very fascinating field. Samsung actually does sell one robot, the robot vacuum cleaner. So we are already a robotics company. And we also have big plans. You can see concept robots here, which have been introduced in trade shows. For example, the Samsung Bot Chef, which is a robot that's so dexterous that it can cook for you. But in order to realize these kinds of concepts, it's clear that research is needed. Manipulation is still a very hard problem, and making something that really is commercially viable is a huge constraint on the problem of manipulation. And I'm not going to say much about that here. I just want to refer you to Dan Lee's talk. He'll talk about the problem of manipulation. And I want to pose this kind of challenge, which is inspired by the fact that there's been a lot of academic progress in research on manipulation, on grasping objects, controlling objects, and so on and so forth. And we've seen these robots on YouTube, various demos, and papers. How come we still don't see manipulating robots in real life? Why don't we have robots that wash the dishes? What is standing in the way of that? Is that just, is it that we already know the basic principles and a little bit of engineering has to be done? Or are there fundamentally new principles that need to be discovered? I think that's a very interesting topic for debate. Now, finally, health and wellness. Doesn't sound like AI. Rather, it's an area where data and devices and AI are coming together to impact human health and living in a really interesting new way. So you've heard of smart this and smart that, you may not have heard of the smart refrigerator. Yes, Samsung has a smart refrigerator. It's called Family Hub. Of course, it has a display on the front, a touch screen. You can interact with it. It has a camera inside. So if you're at the grocery store and you want to see what's in your fridge, do I have milk? You can look inside your fridge remotely. But not only that, the AI can look inside your fridge, and it can recognize some of the food that you have inside your fridge by computer vision. And through knowledge of the food you have, it can recommend recipes to you. It can help you plan your meals. It can help you shop for more groceries that you need to cook and deliver those meals to your family. That's a food AI. And central to the food AI is a very important topic, recommender systems. And here we're benefiting from a collaboration with the Insight Center for Data Analytics, a leading academic center at UC Dublin, led by Barry Smith. And this is just showing one product of that collaboration, which is FedFast, a new twist on federated learning for recommender systems. So federated learning is interesting because it can help speed up learning, can help distribute learning, and can help ensure user privacy. So this is a very interesting area for us, and we're really excited by our collaboration with UC Dublin, which is spearheaded on our end by James Garaci. I want to mention another partnership. Samsung has partnered with Kaiser Permanente, an American health company. And this is a collaboration for cardiac rehabilitation. It's called HeartWise. And so the idea here is that we take patients who are recovering from heart problems and we give them a rehabilitation program that they can do at home through wearables and their phone. Those are taking data about them, and they can interact with their advisors remotely. And through 7 weeks, they can rehabilitate themselves. And this has a big effect on patient outcomes. Obviously, a really bad outcome is having to go back to the hospital. That's called readmission. But you can see that this program has led to a huge reduction in the hospital readmission rate. And that sounds incredible, right? Huge reduction. And my first impulse when I heard about this is to think it's about the heart. But actually, if you look closely, this is all about the head, right? If you look at the effect on these patients, normally only 50% of patients actually complete the rehab program, the typical conventional rehab program. But with this home-based virtual cardiac rehab, 90% of patients completed their rehab, all 7 weeks. And of course, that is quite likely one of the big reasons behind this much improved patient outcome. So this is showing the ability of data and devices to change people's heads, change how they behave. And so putting all this together, recommender systems, data, and devices, you can ask the question, general question, how can AI help us improve ourselves, right? Improving our health is often about changing our behavior. And maybe these technologies can actually help us in that very, very difficult task. And so I'd like to leave you with that thought, and I'd like to express my appreciation to our incredible speakers for coming out today and offering up their latest research in their lectures that we're about to see. So thank you very much for your attention. Thank you for coming. Like all of you, I'm looking forward to being educated about the latest advances in AI. Thank you very much.
Thank you very much for the opening keynote, President Singh. Now, let us continue our forum with a technology session. The first one is the natural language processing session. Well, we have Professor Christopher Manning from Stanford University as our speaker. Professor Manning is a world-renowned expert in the field of natural language processing. He is also a pioneer in the research of applying deep learning to natural language processing. He's a fellow of ACM, Triple AI, and ACL, and he is currently the director of Stanford AI Lab and associate director of Stanford Institute for Human-Centered Artificial Intelligence. Today, he will be presenting on the topic of natural language understanding and conversational AI. So without further ado, let's have a Professor Christopher Manning for his presentation.
Good morning, I'm Christopher Manning from Stanford University, and today I'm going to introduce recent research in natural language understanding and conversational AI. Let me start this talk with people. At Stanford, we have recently established an Institute for Human-Centered Artificial Intelligence. The three themes of the Institute link between people and AI. We believe that for developing the next generation of breakthroughs in artificial intelligence, that firstly, AI must incorporate more of the versatility, nuance, and depth of the human intellect. However, as AI is widely deployed in the real world, we are no longer just technologists in a lab, and the development of AI should be guided by a concern for its impact on human society. Finally, we emphasize AI as the next generation in the development of human tools, and argue that AI should augment human skills, not replace them. Overall, we think it is very important to build AI that supports us in our human goals, but is constrained by our human values. Back to people. People have needs for information, communication, business needs, and social needs, such as to feel that other people get them. They achieve these goals using the most marvelous of human inventions, language. For computers to communicate with us easily, to receive and give appropriate information, and for humans and computers to feel that they understand each other, computers need the ability to understand human languages. Most people primarily use their computers to communicate via human language. Half of the world's population uses both one of the big four social networking apps and one of the big four messaging apps each month. Spoken language interaction is taking off with modern virtual assistants. There are more than 100 million Alexa-enabled devices in use today. Google Assistant is available on over 1 billion devices. The rate of adoption for smart speakers is faster than it was for cell phones. Spoken language is also key to enabling productivity on mobile phones. On these devices, reading is difficult and input on virtual keyboards is tedious. They're even harder to use for people doing a physical task, including driving, elderly people, people who use Chinese characters, and the many people with low levels of literacy. Notwithstanding the awesome texting abilities of teenagers and those in their 20s, spoken interaction with phones is much more efficient. My Stanford colleagues Sherry Wan, James Landay, and Andrew Ng found that speech recognition is now 3 times as fast as texting for such users, even after factoring in the time to correct speech recognition or texting errors. However, while computer speech recognition is now excellent, the understanding of human language utterances lags far behind. And that is the main topic of my research. Sometimes when I ask Siri, what was the final score on the Women's World Cup today, it works beautifully and gives me the answer. But most often when I ask my digital assistant for an answer, I get something like this. How do I see my subscriptions on the iTunes store? I found this on the web for how do I see my subscriptions on the iTunes store? What that means is notice again that the speech recognition was perfect, but the phone is basically confessing that it had no idea at all what I meant. So despite the fact that the answer exists on the support website, it's not able to understand my question well enough to be able to give the answer. And so a lot of the research I do is how to get better natural language understanding to try and push the field forward to allow this kind of language understanding by computers. For any of Command's questions or human knowledge, most of it is in the form of human language material, either speech or text. And we need computer systems that can efficiently understand human languages. Fortunately, there have been enormous improvements in natural language understanding in the last 2 years, driven by the development of a new generation of deep contextual representations. In particular, the BERT model has become very famous as a large language model, though there are now generations of other bigger, more recent ones, including ERNIE, GPT-3, T5, Roberta. These models introduce a new neural architecture. So apart from the left column, all of these models are transformer models. I'm not going to have time today to explain all the details of how transformer models work, but the starting point is that their task is to predict words that have been masked out in a piece of text. So we have Judiciary Committee mask report, and the model wants to guess what word was masked out. And the style of the model is that it is then working out attention scores between each position and every other word to compute information about a contextual word representation. So for each word, it calculates a query vector, which is then compared to key vectors in each position. And then based on those weighted attention scores, you're then combining together a weighted value from each word to come up with a new representation for the word committee. And then these are deep networks with many layers, which repeat this process over and over again. So you get a strongly contextualized representation of the meaning of words and then progressively the meaning of larger linguistic units. These models have been super successful. So basically for any natural language processing task, the state of the art in 2020 is the performance you can get with these large contextual language models. I'll just mention one example here. So the Allen Institute for Artificial Intelligence has worked for many years, well over a decade, on the task of learning scientific knowledge and being able to answer science questions. That's its Aristo project. And in its origins, this was meant to be the task which would lead to the renaissance of research and knowledge representation and reasoning. But what they've found over time is exactly the opposite, as shown in this paper from last year. So for these science question answers, you can get a certain distance with just information retrieval. The knowledge representation reasoning systems can do a bit better than information retrieval, but unfortunately actually often not much better than information retrieval. But as soon as you turn to BERT-style models, you're getting an enormous performance increase. And going from BERT to a later generation like Roberta, you get even more increase. So these Aristo BERT models are just like the regular BERT models, apart from they're trained on a lot of scientific literature rather than general English. And the eventual Aristo system is an ensemble, but as you can see, it's really not much better than the performance of Aristo Roberta. I want to give you more sense of what's powering these results, and then to talk about some work that we've done to try and prove the usability of these models. So I'll show you quite a few results on the GLUE benchmark. And so this was a benchmark of tasks testing natural language understanding. Some of them, whether you can make inferences about text, such as the example here, where Jainism hates nature as contradictory to the fact that hills and mountains are sanctified, or other ones can be things like pronoun interpretation, deciding she is nosy, the she refers to Susan, not Anne in the lower example. For these GLUE benchmark tasks, in the last couple of years, enormous progress has been made. So compared to the models of about 2016, such as based on gloved word vectors, that we've seen the error of these models reduced 3 times, and with successive generations of large contextual language models, performance is getting better and better. Indeed, the performance of the latest models like Albert and Roberta is actually better than the performance that's been measured for individual humans doing the same tasks. However, if we decide to change the x-axis to now look at the amount of compute required to get these results, you start to see a rather different story. So early models like the glove-based and Elmo models used virtually no compute, you'd say, in retrospect. And as soon as one started into the BERT models, either the small BERT model or the large BERT model, you're starting to use massively more compute. So the BERT-based model is using 64 exaflops, 6.4 times 10 to the 19 flops to train. The BERT large model is using 190 exaflops to be trained. So BERT large uses 60 times more compute than Elmo in its training. But that was only the start of things. As we proceed on from there, it's only increased by further orders of magnitude. So the Roberta model uses 16 times as much compute as BERT large, 3 zetaflops. And then even more recent models like Albert and T5 use about 10 times as much compute as Roberta, about 30 zetaflops. And GPT-3 is up there in that range as well. So my colleague Andrew Ng likes to say AI is the new electricity, but what instead we seem to be seeing here is almost the opposite. It seems that electricity is the new AI, that we're getting better results simply by using more and more compute to train our models. So we've been interested in particular my student Kevin Clark, on can we get the good effects of masked language models with less computational resources? Well, one of the ways in which these models seem efficient is that although they do the computation for all words, they really only learn on the masked words. And another way that they're perhaps inefficient is the big softmaxes to predict individual words. So we explored a different pre-training task where we noise the input by replacing some of the words with similar words. And then the model is simply asked to predict which words are original words and which words are among the minority of replaced words. And for both of the reasons given, this is a much more energy efficient way of doing pre-training of large language models. And so we can use a fraction of the compute and produce models that work as well. So if we look at largish models of a large size architecture, we can build something that requires the amount of training of a BERT large, but works considerably better on question answering than models that take 5 times as much training. And if we head into the small, we can start building smaller and smaller Electra models. So we can build a 6.25% Electra model, which can be trained in hundreds of times more quickly than a BERT-based model. And its performance isn't perfect, but its performance is still pretty good, better than an Elmo's model by several percent. And is then of the kind of small size that any graduate student can train. It only takes 6 hours to train on a single GPU. Let me now turn back to conversational AI systems. A very real possibility is that virtual assistants will replace the current phone or computer screen-based internet. Assistants will be able to execute tasks for us on many devices, often in a hands and vision-free way. Traditionally, speech dialogue systems have been mainly handcrafted rule-based systems. They use a little machine learning for intent recognition, but then they're largely followed by templated generation. Can we now use deep learning to build such systems? This is a project that a number of us at Stanford are interested in under the Open Virtual Assistant Lab that's led by Monica Lam. I'm going to mention a couple of pieces of work, one on training task-based dialogue by Giovanni Campagna, and then looking at aspects of our conversational social bot. So for task-based dialogue, we'd like to have flexible natural language programming so that we can go from human language intents to a formal programming language representation that we call the Virtual Assistant Programming Language, or VAPL. And the secret is we'd like to be able to build these systems that work for all sorts of niche tasks, so that every time someone has a new Internet of Things device, a new light or alarm or toaster, and every time someone sticks up a new web API, it's not that we have to then say, oh, we have to build a training set of 50,000 natural language utterances. We can very quickly get a natural language interface working with that system. And the question is, how can we do that? And so that involves building a neural semantic parser that can translate from natural language to instructions in the VAPL code that will execute the correct command. And this work is looking at coming up with a method, Genie, which lets us successfully build neural semantic parsers without requiring a huge amount of hand-labeled training data. Traditionally, semantic parsing has been hard because it only works well if you have lots of annotated data with which to train the neural network. And that's very expensive and impractical for this new world. So the idea of Genie is to be able to generate good quality annotated training data at scale relatively cheaply. How do we go about this? Well, the starting point is that Genie has an API library. So these are the different commands that it can actually execute inside the VAPL programming language. And for each of these commands, there'll be a basic natural language realization of it. My Dropbox files in X or post X on Facebook. But the advantage of having a formally specified programming language is then we have compositionality through the programming language, which can then also lead to compositionality of the natural language. So when we combine things like, when there is a cat picture posted on Facebook, we can compose together the basic API calls with VAPL language constructs and produce at least an awkward natural language form for it. We then want to be able to get beyond that. So we start off with synthesizing a large number of expressions just using the data that there is, but that won't show us the whole range of natural language. So we do a couple of things. One is we do actually collect some human data. We ask humans to paraphrase some of this data that we have synthesized, because that does unlock parts of human language capabilities that we can't discover by just composing in a rule-based way commands. The second thing we can do is greatly expand the data by augmenting it with entities and paraphrases, so automatically changing things using other person names or other phrases we know to be similar. So using this idea, we can produce a huge data set of 3.6 million augmented training items, despite only getting a very small number, about 24,000 human-given paraphrases, so only costing about $8,000 on one of the Turka platforms. We then use this data in a neural model where we're using a modified Decker NLP model, the model developed by Brian McCann and colleagues at Salesforce for semantic parsing. And this shows you some idea of how it works. So we compare in the light blue the baseline model that's just trained on supervised data versus the effectiveness of the Genie model. And what we find is that the baseline model just doesn't generalize very well, and its performance on the test data is quite poor. Where the Genie model is general, its performance is much better, and its generalization capability is much better. And this is testing on real user data collected from if this, then that. And I mean, actually, the only previous work using this data set as a test set got almost no performance. It only got 3% performance. But human language isn't only about giving tasks and commands. A lot of human language is about chatting. And we've also been working with some of my students, Ashwin Paranjape and Abigail C, on building a conversational social bot. Most social bots aren't very good at the moment. They have too little user initiative, forcing people into rigid dialogue trees. They can only chat about a narrow range of topics. They don't support niche interests. They provide information, but not in a conversationally natural way. And they don't show interest or empathy for users' experiences and emotions. And so the result is you have unengaged users. So what we'd like to do is instead have a social bot which allows the user to drive the conversation. It chats about any topic, provides information conversationally, and engages empathetically with users' everyday experiences and emotions, resulting in engaged users. And so the mechanism that we've been exploring to do that is making use of a neural generator to produce natural chat about a user's personal experiences and emotions. So the bot does start off with a handwritten starter question, but after the user responds, we're then generating responses using a neural language model, a GPT-2 model that has been fine-tuned on empathetic dialogue conversations. And that allows us to quite naturally follow along a conversation with the user for several turns. Eventually, these models do tend to degrade. And so part of what we then do is cut things off and return to sort of a hand-guided new direction to take the conversation. We wanted to do a bit more to encourage sharing and emotional conversations. Neural models work better when users give longer, more contentful utterances. So we tried some conditions to encourage that. We tried talking about the bot's own feelings before asking a question, sharing personal anecdotes, and these are indeed effective methods to get the user to give longer responses. And so the result is that we have a model that can chat about any topic. So the average user talks about 8 different entities on the conversation, and about a third of the conversations have at least one rare entity, these ones over on the left side of this graph. And indeed, people are happier with their conversation if they've gotten to chat about some rare entity. Okay, there's just one more example of natural language use that I want to touch on before concluding. This example is a little bit different. It's showing how natural language can be useful in medical applications. A lot of the application of AI to medicine has concentrated on doing visual tasks, of doing various kinds of processing of images. And that's a great goal, but the problem is annotations are very scarce, and it's hard to build up large data sets of getting doctors to provide training data for images. So typically, the two main methods that are used just to little label data and transfer from general data sources like ImageNet, but that suffers from drastically different image characteristics, or to look at the textual reports that doctors do write anyway, and to do rule-based extraction of labels, enabling supervised learning. But that's inaccurate and hard to generalize and scale. So what we've been exploring is whether you can do much better with unsupervised learning. And people have tried this for image-only unsupervised learning using methods like SimClear and MoCo. But because the images tend to be highly similar, that tends to be an ineffective objective. So our idea is, well, doctors write narrative reports on what they find anyway. So can we just use these natural language reports as effective additional material to drive unsupervised learning about images? And so that's what our model, contrastive visual representation learning from text, does. The core idea is that we're combining images with true and wrong natural language reports about them, and then we're doing contrastive learning to maximize agreement on the true versus the false image text pairs. So we pre-train on 2 medical data sets and we evaluate their performance on 4 medical image classification tasks. And what we find is that using this much superior form of pre-training, we can then work with much less hand-labeled data, about 10% of the amount of hand-labeled training data of other methods, and outperform other methods on this task. In particular, if you compare the unsupervised pre-training with language versus vision-only unsupervised pre-training, the middle 2 bars in each diagram, pre-training that involves language is much more effective. Okay, let me just now close with a final thought on the role of human language and artificial intelligence. When thinking about artificial intelligence, people normally fixate on modeling an individual human brain. But human language is powerful precisely because it gives groups of people a way to network human brains together. In fact, an individual human may not be much more intelligent than a chimpanzee or a bonobo. These monkeys have been shown to also possess many of the hallmark skills of human intelligence, such as using tools and planning, and they have better short-term memories than we do. Within the history of life on Earth, human beings developed language really recently, but the power of communication set off our ascendancy over other creatures, even though we aren't as strong as an elephant or as fast as a cheetah. It was much more recently again that humans developed writing, that was about 5,000 years ago, allowing knowledge to be communicated across distances of time and space. In just a few thousand years, this information sharing mechanism took us from the Bronze Age to the smartphones of today. The power of language is truly fundamental to human societal intelligence, and hence to the future of a world with artificial intelligence. Thank you very much.
Thank you very much, Professor Manning. Thank you very much. We learned a lot from your presentation. In this lecture, Professor Manning has introduced some work on natural language processing and conversational skills which conform to the human values. And he also emphasized that just like the exchange of information through language has significantly improved a civilization, understanding and utilizing natural language is also very crucial in the AI research. Well, coming up next, we have Devi Parikh, professor at Georgia University of Technology. For the second technology session, she has prepared for us the vision session, where we will hear about multimodal and creative AI system. Professor Parikh is a professor at Georgia Tech as well as a research scientist at Facebook. Her main research area lies in the intersection of computer vision and natural language processing. And she has received the Sky Computers and Thought Award and Sloan Fellowship, and has been selected by Forbes as one of the 20 incredible women advancing AI research. So from now on, let's enjoy the lecture.
Hi everyone, my name is Devi Parikh. I hope you're all doing well. It's too bad that we couldn't be with each other in person, but hopefully we can do that again sometime in the near future. I hope you're all safe, and thanks for tuning in to listen to my talk. And so I'm going to talk to you today about some work we've been doing with multimodal AI systems and creative AI systems. And so let me start with the first part on multimodal AI, and by that I mean vision and language. And so I mean tasks like given an image like this, we might want to automatically describe it in a natural language sentence like you see here. Or given an image like this, we may want to describe the different regions in the image in brief descriptions like you see on the screen, or given an image and a natural language phrase like the toy with pink hair, we may want to draw a bounding box around the region in the image that's associated with this description. And it might not be just static images. There might be a video that we may want to describe in high levels of detail, like you see here, or perhaps a shorter description in a few sentences, or even a single sentence description that captures the gist of what is going on in the video. It may not just be descriptions. We might want systems that can answer natural language questions about images. For example, what is the kid doing? We may want to be able to answer this question automatically and say the kid is skateboarding. And it might not be just a static single question, but there might be a back and forth conversation where the system might start with the description of the image, and the user might have a follow-up question. Is the motorcycle moving or still? The system might answer its part, and this conversation can continue from there. And so the reason these problems at the intersection of vision and language are interesting is because there are several applications that can benefit from these. So for example, for aiding visually impaired users who may not have access to the visual modality, if we have a way of translating from this visual modality to language, then through language, these users might be able to extract information about the visual signal. If you want to navigate through large quantities of unstructured data, language is a natural modality with which you can interact with it. A lot of the information on the web is inherently multimodal. And so having ways of connecting vision and language can allow us to extract information, richer information from the web. A lot of the content that might be on the web, if you want to identify hateful content, these problems tend to be inherently multimodal, but it's not just about the vision, it's not just language, but you need to reason about both to be able to make these assessments better. If you think of AR, VR applications, again, having the visual world and language connected can be useful for these applications. And so in this space, we as a community have made a lot of progress. We can now take images like this and automatically describe it as a man in blue wetsuit is surfing on the wave, or an image like this, a group of young people playing a game of frisbee, or a car is parked in the middle of nowhere, a pot of broccoli on a stove. And these are all automatically generated descriptions as of a few years ago, which is quite impressive. Even in visual question answering, we can take images that look like this. And if there's a question that says, what is the cat wearing? We can automatically answer it by saying hat. Or for this image, what is the weather like? We can automatically answer it saying rainy. What surface is this? Clay. What is the weather like? Sunny. What color is the cat's eyes? Green. What toppings are on the pizza? Mushrooms, and so on. And so we've made a lot of progress on a variety of these tasks over the years. But one thing that has led to this progress is this recipe of training task and dataset specific models. So for every task that we care about, let's say visual question answering, a group of researchers, in this case, my students and I, we collected this large data set on visual question answering, and we trained models specifically for that task. And so now we then had a model that can answer questions about images. But now if we want to do image captioning, then we sort of follow the same thing again. We collect a new data set for image captioning, train a model specifically for that task, and then we can have an image captioning model. Visual common sense reasoning or referring expressions. So for any one of these tasks, we collect a separate data set, we train specific model architectures, and that's how we've made progress on many of these tasks. And so what's dissatisfying about this approach is that you would think that there is a common set of visual linguistic representations that you can just learn. You can learn them once, and then you should be able to apply these to a variety of tasks. And that's not what's been happening. For each of these tasks, we end up learning a different set of visual linguistic representations. And so as a result, what might happen is if you ask a VQA model, what is the man making? The VQA model might say cake, which is not quite right, but that's what it thinks. And if you feed this image to a captioning model, the captioning model might say an older man is wearing an apron and making pizza. And so this suggests to us that these two models have learned a different set of grounding for the regions in the image. The VQA model thinks this image is about a man making cake, but the caption model thinks this image is about a man making pizza, which is not quite consistent and is in that sense quite strange. So what we wanted to do was to see if we can learn a common model for visual grounding. And so once we learn this common model for visual grounding, we can use it for a variety of vision and language tasks. And so that's where we had this model called Wilbert that we presented at NeurIPS in 2019, where the setup that we were looking for is we wanted to be able to pre-train these visual linguistic representations, so pre-train these connections between vision and language once. So you do this pre-training once, and then you can fine-tune this for a variety of downstream tasks that you might care about, whether it's answering questions about an image or image and caption matching or any one of those things. And so one thing we need to think about if we want to pre-train these visual linguistic representations is what source of data we can use to train these models. And so in this work, we used conceptual captions that has 3.3 million images and associated descriptions from the web. Another thing to consider is that the two modalities, vision and language, tend to be at two different levels of abstraction. So on the vision side, sort of these low-level pixels, each pixel individually doesn't have much semantic meaning. Whereas on the language side, if you look at individual words, each word already is fairly rich in terms of the meaning that it captures. And so we need ways in which to bridge these two modalities and deal with the fact that they can be at two different levels of abstraction. And so we propose this two-stream model that tries to work with this, and the details of that are in the paper. Another thing to consider is how we can combine information across these modalities. And so we have a co-attention mechanism that, based on the visual information, attends to language in an appropriate way. And based on the language, it attends to the visual signal in an appropriate way. And so with all of these pieces together, we're able to pre-train these visual linguistic representations and then apply them to 5 different downstream tasks. And what we found at the time was that this approach outperforms state-of-the-art on all 5 tasks. And what's nice about this is that all of these tasks have a common backbone, a common set of visual linguistic representations that are consistent across all of these tasks. And you then have this downstream performance that is very accurate. So that was nice to see. We then extended this work where instead of pre-training the model to learn these visual linguistic representations and then fine-tuning it for each of these different tasks, we wanted to see if we can have the same model be applied to a variety of different tasks. And so in this case, we had one model for 12 different tasks. And what we found was that this performs higher than what you would get if you had trained an individual model for each of these tasks. And so what that means is you essentially have higher performance for 1/12 the model size, which was quite nice. And on 7 of these tasks, we had state-of-the-art performance. And so now you have one model that, given an image and a question, can answer the question. Given an image and a caption, it can give you a score for how consistent the two are. Given an image and a phrase, it can draw a bounding box around where that region is described, and a variety of other things that you see on the screen here. So what I will do next is I'll show you this online demo that we have. You're welcome to check it out yourself. It's on wilbert.cloudcv.org. You can upload your images and try a variety of tasks. And so here, let me walk you through this demo on a few examples where we can first upload an image. And as I said, you can try this with any images that you like. And now on this image, you can pick one of these several tasks. Here, we're going to ask a question that says, where is this picture taken? And so this model says kitchen. On the same image, we can ask a spatial reasoning question, like what is behind the man? And the model says refrigerator. We can now do a pointing question, like which object is red? And the model will point to the different objects in the image that are red, like the t-shirt and the apple and so on. You can do a referring expression where you give it a phrase like the boy, and the model is expected to draw a box around that object. So you see that you're seeing a box around the boy. If you now make it the girl, you should see bounding boxes around the girl in the image. We can do a referring dialogue where we can now ask for an object that's edible and is red. So is it edible? Yes. Is it red? Yes. And so it finds the apple, which is the red object in the image that's edible. If I now say, no, it's not red, but it is still edible, the box is now around the bananas, which are edible but not red. We can do a visual entailment where we can give it a statement, and the model will tell us whether the statement is a contradiction or neutral or true with respect to that image. We have some tasks that need 2 or more images. So here's a task that needs 2 images that we just uploaded. And for this pair of images, we'll give it a caption that says both images have 3 people in them. And the model says that's false because it's not true. It's not the case. The image on the left has 3 people in them. And the model says that's true. And if you now say the image on the right has 3 people in them, the model should say that's false. We'll now do one last task where we upload these 4 images. And it's a retrieval task. So I will, as input, provide a description, and the model will sort the images based on how much they match the description. So mother and daughter, and the model will now sort the images based on which image is closest to a description of mother and daughter, father and 2 kids. The model is resorting the images for this description. That makes sense. A street scene. And so these same 4 images are being sorted based on the input description, the input query that we're providing. And you can see that the responses are quite meaningful. A peaceful scene. Boy is handing a can to a man. And so the top left image should be the most relevant to that. And that's what the model says. A girl is flying a kite on the beach. And so you can see that the descriptions can be somewhat abstract, like a peaceful scene, or it could be naming the scene or the objects that are in the scene and so on. And so that those descriptions have been reasonable. And so as I said, you're welcome to check this out yourself. In this project, we're interested in taking as input a piece of music and producing a visualization or a set of movements where the movement is synced with this input music. And so it has this illusion of being a dance, if you will. So this is one example where I'll play the music that was the input piece of music, and you will see this abstract pattern move in a way that hopefully looks like it is synced with that music. And here's another example where it's the same approach, it's the exact same algorithm, except the visualization now, instead of being this abstract pattern, is a stick figure of a human. And so this might look a little bit closer to what we're used to thinking of as dance. And so I'll play this again, where you'll hear the input music, and the stick figure will move in a way that should roughly look like it's synced with this music. And so one project that we have in this space is called thematic typography, where given a certain word like book and a theme library, we want to write the word out in that theme. So in this case, we are replacing the letters of the word book with icons that look like those letters, but are actually pictures that represent the theme library. So here's another one. The word is car, and the theme is driving or road signs. Here's another one where the word is witch, and the theme is Halloween, or the word is play, and the theme is Olympics. This is another project that we've done in this creativity space that's called Lemotif, where as input, we are given a description from a user of what their day was like, and we can automatically extract what the topics were that were being discussed in this description and what emotions the person seems to be describing around those topics. And we generate automatically this visual abstraction where the topics are displayed as these different shapes and the emotions are displayed through these different colors. And we have this visual abstraction based on that. This is one visualization. We have several others that we've experimented with, but that's the general idea. We've also done some work on neuro-symbolic generative art, where we start with generative art or visual patterns that have been produced by a procedural generative process. And then we train a neural generative model on top of that to produce these visual patterns that have this different organic aesthetic to them. That is a combination, sort of a hybrid of the neural generative aesthetic and the procedural generative aesthetic with which the original training data was generated. We've also done some work on looking at collaboration in the context of creating sketches, where there's one canvas and different people can come one after the other and contribute strokes to this canvas to create a picture. And we've studied what happens in different collaborative settings. So at one end of the spectrum, you have this individual setting where one person has drawn the entire picture. And what we find is that there tends to be a variance in quality based on the skill level and the motivation of the individual creating this picture. Where some of these are quite nice, whereas other ones are perhaps not all that nice. But overall, it sort of tends to be a little boring that even when the picture is nice, the topics and the themes might be similar to what one might expect. The other end of the spectrum is where multiple people have all contributed to a picture. So one after the other, 30 different people come in and contribute strokes to the canvas. And what we get looks something like this, which is quite intriguing. It's very different from the pictures that you see on the left, but it tends to be sort of a little too chaotic and too noisy to extract any meaning out of it. And so we propose this in-between setting that has this collaboration component, but also has a voting mechanism, which gives us these interesting and rich pictures, but they're also quite coherent and sort of they tend to be less noisy and less chaotic. And so all of this was studied in the context of human-human collaboration, but the hope was to be able to extract, to be able to learn from what we find here and use that to design human-machine collaborative systems. And so to summarize this part of the talk, I think creativity is important. It's at the core of all progress that we make. Creativity is also sort of considered to be a deeply human experience. And so if we can have ways in which AI can assist humans in this creative process, that can be quite powerful. It's an intriguing AI challenge. As I said, it's a powerful use of technology. And at its core, it has human-AI collaboration, which I think is quite exciting. So overall, to summarize my talk, I talked about two different themes within this context of human-centered AI. The first was problems at the intersection of vision and language, which can be thought of as having natural language interfaces with these computer vision systems. And the second is this idea of trying to use AI as a way of assisting or enhancing human creativity. That's all I have. Thank you.
Well, thank you very much, Professor Debbie Parikh, for your wonderful presentation. Well, she has explained about some applications that require both visual input and natural language input simultaneously, along with the visual linguistic model, which enables those applications. Also, she emphasized the importance of having an AI system that can predict and consider assumption models that the human expects, which is central to effective human-AI collaboration. Now we'll have the Q&A session with our two speakers and the technology session 1 and 2. And this will be led by President Sebastian Singh.
Hi, Chris and Devi. Thanks a lot for your wonderful presentations. I want to start with one question, which is just one of clarification. So we have a question here. Why is softmax a problem for making a lightweight model? This is, I guess, for Chris.
Okay, that's a very straightforward, simple fact. I mean, that's simply that, you know, vocabularies are very large, right? So it's like a sort of an extreme classification problem with a lot of classes whenever you're trying to generate words or even word pieces. And that just simply means that in the softmax, you've got a very large matrix multiply simply to sort of work out the probability distribution of the different classes. And, you know, well, it's not that that's impossible. We do a lot of matrix multiplies, but nevertheless, it turns out those softmaxes become a significant part of the total computational burden of these models.
Great. Yeah, so this is a problem that's come up in a lot of past work too, right? So it's a well-known issue. So Devi, we have a question here, which is simply, how do you measure the level of creativity in AI systems, or I guess also in humans? You answered this online, but maybe you could address that here, the evaluation. What is the cost function, or the objective function?
Yeah, happy to do that. It's a great question, and I don't think I can provide a cost function that you can write down as an objective function to optimize in the context of creativity. So this is one of those questions that's been debated extensively, not just in computational creativity, but also in cognitive science and philosophy. What does it mean to be creative and so on? And as far as I know, there isn't a well agreed upon answer to that. It continues to be a highly debated question. Sort of practically in our work, the way we've approached it is to think about creativity as a combination of novelty and value. And this sweet spot is important, right? You can be just random and as a result be novel, but you may not be valuable. It might not be a high quality artifact. And similarly, you can be valuable, you can be high quality, but if there's nothing new about it, then it's not going to seem creative. And so this combination between these two things that can be at odds is what we've thought of as creativity. And this is a definition that's frequently used in computational creativity literature. And so we approach it with human studies where we have human subjects assess whether a certain artifact seems novel, whether it seems of high value or high quality, and then artifacts that hit a good compromise between the two is what we assess to be creative. But this is very much an open question, and the answer to this will depend on the domain, if you're talking about poetry or dance or paintings and so on. So there's a lot to think about there.
Great. Chris, another question that came in was, is there any notion in sort of real world natural language systems, is there any notion of debugging? You know, if you look at the errors that the system makes, let's say the system flubs a question about US presidents. Do people look at those errors and debug, or do they just forget about the errors and just try to make a better model next time? What actually happens?
That's a good question. And, you know, among all the debate of the strengths and weaknesses of neural models, I mean, honestly, this is one of the weaknesses of neural models because, yeah, I mean, absolutely, people run systems on data sets and try to look at features of different data sets so that you'll commonly, you know, have different kinds of questions or different degrees of out of domainness or text, and you try and see how the model performs. But, you know, commonly, it isn't actually very easy to see how to fix individual errors. So, you know, in the previous sort of decade of work with the sort of hand-built feature-based models used in machine learning systems, often if you saw errors of a particular sort, you could be easily creative and think, oh, what I could do is add in some new features that looked at this, and it'll help with those examples. And that worked pretty well, whereas it's actually not so easy on the neural systems. I mean, sometimes error patterns have sort of motivated new architectures and things like that, but it can be hard. You know, in a lot of commercial systems, the crude bottom line is if the model is making mistakes in certain places that are somehow problematic, that people will just override those errors in straightforward rule-based overlay methods. But that's perhaps not the exciting answer that you're hoping for.
All right, so that in the real world, people do put in these exception handling things. Okay. Well, this is a question for both of you. Both of you talked about multimodal applications using both images and text together to be more powerful. I'm curious if this question is for both of you. Do you want to compare and contrast your approaches?
Let Debbie go first.
Or you could also talk about what do you think that is a major important direction for the future? The other common thing is the use of transformers. So I guess somebody on this forum asked, has transformers killed off everything else in NLP? Is there hope for it? It was kind of, is there hope for any other approach? It was kind of this besieged kind of question.
Chris, do you want to take that one?
Okay, I can make some comments. Yeah, so I think now there are at least a couple of ideas that really motivate bringing language and vision together. So exploring multimodal learning is a really interesting problem. But another thing that's a really interesting problem from the language point of view is looking at grounded language learning, and the most natural way to ground language is respect to visual world. And so it's an area that a ton of people are interested in. There's lots of things that can be done, and I'm sure there'll be a lot more of it. And there are different ways you can then start going. I mean, I think it's important to remember, at least from the language-centric point of view, although vision is a very natural complement and a very good way of grounding, it's certainly not the only way that happens with language systems, that we have lots of concepts of other kinds, whether they're from our imagined worlds or math or whatever, where the grounding is something other than vision. So for the part that I've been involved in different things at different times. So I've, also worked on the kind of visual question answering area that Debbie is very associated with. But for today's talk, what was different for me was this idea of how language can be used as a form of labeling. So that the main thing has been that, oh, gee, we want to do some tasks and let's go off and label a lot of things, and then we can build classifiers. But, there are lots of things in the world that people talk about or write about, like sports games, people's speeches, or in this case, it was chest x-rays. And so if you can regard human language as then a sort of labeling, and if you can exploit that, that's wonderful, because then that can give you large quantities of data for free.
Just running with running with the grounding idea, I guess, Debbie, you got a question about common sense. Maybe it's a big question. So do you feel like the vision language thing is the right way to get grounding in common sense?
I do think it's a step forward. So like I was saying in my response there, that one way of thinking about common sense is to say that if something has been talked about frequently in text, then that is sort of normal. And if something hasn't been talked about frequently, then that might be the unusual thing. But there's an issue with that line of thinking in that reporting bias has been well studied, where if something is commonly known, then people don't usually have a reason to talk about it in text. And so a lot of the frequent things you might not find as frequently in text. And so there's something like having this other modality like vision or other perception signals could help, where they might suffer less from this reporting bias. And so looking at both vision and language and perhaps other modalities could help with this common sense reasoning more.
How are we doing on time? How much time do we have? Oh, 5 minutes? Okay. Chris, I've got a question about your Open Assistant project. So,
Sure.
is the goal more to make it open, or is it to make the assistant better than the closed ones that exist today? Or do you think that those two are related goals?
I think in some sense they're not very clearly related, but they're both goals. So it's no doubt at all that part of what we're wanting to do is have something that is open. And so that it's just, we are at this place in the world at the moment where we seem, for people who are old like me, once upon a time, there used to be a few closed gateways to online information services. So in the US, there were ones like CompuServe and AOL, and I'm not actually so sure what there was in Korea. And so compared to that, the internet was this wide open world with a million different websites and different entry places. And it seems like, unfortunately, now we're going in reverse, and we're entering this world not only where there are a few websites that occupy most of people's time, or web services, things like Line or Facebook or whatever, but especially in the voice world, that it's really dominated by two huge players, which then control what are all the services available and how you can interact with them. So I think the openness is really important. But that's sort of orthogonal to, as researchers, it seems like, hey, if we're going to be doing this, it'd be nice to be exploring a different part of the space and trying to do something different. And that sort of then motivates some of the explorations of having a conversational, empathetic chatbot rather than the kind of more command-based systems that you see now and things like Google Assistant.
Right, but I guess the question is, some people might ask, do you really have a chance of beating big companies and making a better assistant? And I guess one question that you could ask would be, how successful do you think those big companies' assistants are? Because I think it's true that the questions that people ask them are pretty limited still, right?
Yeah. So in one sense, they've been, quite successful, right? So the rate of adoption of having virtual assistants is faster than the rate of adoption of mobile phones. We almost forget now, but actually, mobile phones took a long time to take off and be used before by more than a few people. So they are succeeding, but yeah, normally their usage patterns are very limited. There's play music, set a timer in the kitchen, make a note. There's really sort of a very simple set of commands. So I think there's lots of room to explore more. But, I think our job in academia is to sort of explore and present different ways the world can be. I mean, ultimately, it's just not possible that we can produce a system with a range of skills and abilities as a company who has 10,000 people working on a system, as is already the case with the big virtual assistants. But that doesn't mean that, these inflection points can't change the world. I mean, a good example, if in a different space, of something that did that coming out of Stanford was actually the exploration of OpenStack networking. So that networking systems were completely controlled by big companies, mainly Cisco, of producing these dedicated networking boxes. But people at Stanford showed, no, these days you can just have all all of your networking logic running on a off-the-shelf PC and connect it to a switch, and you can then do interesting things. And, you know, that changed the game, and then commercial players got into that space.
Great. Continuing on the theme of big tech and social implications, we have one question for Devi. Social media sites rely on autonomous algorithms that are very effective. How will AI impact or enable social manipulation?
So that is a difficult question. There's a lot of people thinking about these things. I'm not an expert in that space, but there are a lot of tasks in that space that AI can help with. Things like spread of misinformation, detecting hateful content. And this is one example that I gave in my talk, where it's often the case that hateful content tends to be inherently multimodal. Like if you think of hateful memes, then the picture by itself might be fine, the text by itself might be fine, but there's something about the combination of those two together that makes it hateful. And so you really need to understand both the language and the image. And in these cases, also a lot of social context, right? Just the cultural connotations associated with these things. And I think using that external knowledge to make these assessments, I think is a significant challenge, and I don't think we've made a lot of progress there. So I think there are a lot of important AI problems to study in that space.
Well, thanks a lot. Thanks for the great Q&A. I guess we'll close on that thought about AI as a potential way to deal with hateful memes, very important in today's society. And let's move on to the next session.
Okay.
Thanks, Devi. Thanks, Chris.
Thank you.
Well, thank you. Thank you very much both for your kind answer about the questions. So before we move on to the next session, we're going to have a quick break, about like 7-8 minutes. And next session will be starting at 10:40. So please stay tuned. I'll see you there. Thank you. Welcome back, and I hope you enjoy your break. Samsung AI Forum 2020 Day 2, hosted by Samsung Research, will be continuing with the third technology session. As our third technology session, we'll be hearing about human-robot interaction. Professor Subaru Kambambati from Arizona State University has prepared this session. Professor Kambambati is currently a fellow of AAAI, AAAS, and ACM, and has served as the AAAI president for 2016 to 2018. He has also contributed as an early member of Partnership on AI, the world's first AI council. His current interest lies on the challenges regarding human-aware AI systems, and so is working on solving the fundamental issues on planning and decision-making. Today, he will be presenting on synthesizing interpretable behavior for human-aware AI system. So, please enjoy his lecture.
Hi, I am Subaru Kambambati from Arizona State University. I'm very pleased to be able to talk to you all regarding AI and the interactions between AI systems and humans today. I understand you're all over the world, including, of course, in Samsung headquarters, and I'm really looking forward to share my thoughts on this today. So today, I want to talk to you about how AI systems can interact with humans fluently, help them, collaborate with them, team with them, and be comprehensible to them. So my talk, of course, is titled Synthesizing Interpretable Behavior for Human-Aware AI Systems. Let me get started. So AI is, of course, all over the place right now. We hear so many things about, positive as well as negative hype, comparing AI to electricity, comparing it to fire and electricity, AI being compared to God on one side. So there are all this, high positive hype. There's also a bunch of worries that people have about AI potentially being a big threat to the civilization and what sort of societal impacts it might have and so on. Among all the news items that you keep seeing about AI, the things that I actually like, the kind of advertisements that I like are these sorts of ones where, AI is helping an old lady cross the street, AI is playing with kids, basically hanging around with humans without making a huge fuss. So I want AI systems to be able to work with humans in a fluent and transparent way. Now, if you're wondering how come this particular breaking news was not seen by you, that's because it's fake news. I just made it up myself. But the question that I had to myself is, why is it that the AI as a field hasn't worked as much in the beginnings at any rate on getting AI systems to work with humans in a transparent and a fluent way? It's almost AI has a curious ambivalence to the humans. It looks as if our systems are happiest either far away from humans are in very adversarial stance with humans, essentially creaming us in every possible board game at any rate right now. So it's almost like, as John Lennon once said, we seem to want to help humanity. Somehow it's the people that we AI folks don't seem to be able to stand, which is kind of disappointing. So in fact, some time back when I gave a presidential address at Association for the Advancement of Artificial Intelligence, I basically chose as my topic the challenges of human-aware AI systems. And I was looking specifically at how come we are not taking it more seriously and what are the challenges in it. Is it really worth the endeavor for AI systems to be interested in AI researchers to make the interaction between AI and humans be more fluent, and what are the technical challenges and what are some of the long-term issues. I was talking about this, and one of the things I try to get across, and I try to get across to you here too, is that in fact, AI systems working with humans makes it sort of expands the reach and scope of the overall AI enterprise. After all, there is this evolutionary theory which says that we did not develop these huge brains we have to run away from the tigers of the savannah or the lions of Bengal, but really to work with each other, strategize with each other, and essentially be able to have this social intelligence is one of the reasons why we apparently developed this kind of a large brain. And so I'm interested in talking about human-aware AI systems. And of course, human-aware AI systems are needed all over the place. There are, of course, areas where AI systems have to interact with humans pretty much from the get-go. Intelligent tutoring systems, for example, social robotics. These are areas that actually, to some extent, looked at how to deal with some of these issues of making AI systems work with humans. But then I want to get you to understand that those are not the only areas. In fact, any time AI systems are in our midst, actually in the midst of humans, they essentially need to be aware of humans. So that requires assistance, human-aware digital personal assistants. Imagine how nice it would be if my Bixby on my Samsung Watch, for example, was able to keep track of what it is that I'm trying to achieve and then provide its answers in a much more context-specific way. Human-aware office and hospital assistants, and then, of course, teaming, elbow-to-elbow teaming between humans and robots on factory floors, remote and cognitive teaming, such as in search and rescue with commanders somewhere in a safe place and the robots in the rubble, for example, and even things like self-explaining factory robots. So in fact, I tend to think that increasingly, if AI is everywhere, then human-computer interaction really will be human-AI interaction. And so we need to understand in what ways human-AI interaction can be made more effective and what are the challenges involved in that. And so my question is, what does it take for an AI agent to show interpretable behavior in the presence of human agents? And the simple answer, and then of course I'll take longer time to elaborate it, and you probably understand this too, that the simple answer in trying to, the way we try to get along with each other is managing mental models. And that's what AI systems have to do. For example, starting from as far back as Salian test, we know that social intelligence involves, for example, the agent realizing that the human has potentially different beliefs than it has, and using that knowledge to actually take that knowledge into account in synthesizing its behavior. This is something that we will talk about in concrete terms. So the overview of my talk essentially is just trying to get across the following points. I want to get across that effective human-AI interactions requires AI systems to be able to manage mental models they have of humans. And these involve essentially first as well as second-order mental models. So humans' models of their own tasks, as well as humans' model of the robot and its tasks, or the AI system and its tasks. And then I want to tell you how managing mental models brings up both inference and learning challenges, and I'll talk about some of those challenges. In particular, we'll talk about how to get explicable behavior, how to generate explanations, and how to handle these things when there are vocabulary differences. And finally, frameworks for human AI interaction have to be evaluated with actual human subject studies, because it's not very reasonable for a bunch of AI engineers to assume that since they are humans, they know what would be acceptable to other humans. And so there are actual fields that look at human factors and human interaction, and we need to actually do these studies, careful studies. And then I'll end with a little discussion about the fact that once your systems are able to mental model the human in the loop, that allows them the ability to manipulate the humans in the loop. And so, in fact, we are always worried about head fakes, but deep fakes. But really, head fakes are the worst form of deep fakes, that the most powerful forms of deep fakes. And we really want to think about how those sort of ethical challenges can be handled. So that's the overview of my talk, and I'll try to get you through some of these points. So let's get back to like a robot or an AI system, essentially trying to figure out how to achieve some goals that it has set for itself or what's given to it. And if it's a single agent, in a simple scenario, let's say there may be, it has its own model, MR, which is the robot's model, and then it uses that to come up with a behavior, a sequence of actions that will take it to its desired goals. There could be more general ideas such as, policies, but, for our discussions, this is a good place to start from. Now, the moment you put a human in the loop, now it turns out that the human has their own model of the task, and the robot then has to have a sense of that model of the task. That's how it figures out the human's intentions, goals, and use that to provide assistance to them, at least avoid getting into their way, and sometimes try to team, etc. This part, which is essentially, this is one mental model, which is getting the model of humans' beliefs, desires, and intentions, and as well as their actions, task actions. That's the first type. In some sense, that kind of has gone under the description of intention recognition, for example. And so there are multiple ways an AI system can recognize the intentions of the humans in the loop, unobtrusively, hopefully, or sometimes with some help. In this particular case, actually, in the examples that, from our lab, we're using emotive BCI interfaces, brain-computer interfaces, not the type of neural link ones, but the simpler ones, to essentially guess what people are trying to achieve. In this particular case, for the robot, is trying to use that information. And in fact, the similar kinds of things can be done similar kinds of technologies can be used. For example, a HoloLens technology can be used in addition to simple, voice and pictures by computers, by AI systems, to project their own intentions. Again, another study from our lab. Okay, now that is the first order, but the second order is actually more interesting from the point of view of my talk today. So the robot essentially has a model, obviously, and the humans always try to model anything that they're interacting with. So if they're interacting with an AI system, they're going to have a model of that AI system. So in this particular case, the human has MRH, which is their own approximation of what they think the robot's tasks are, actions are, and goals are, and preferences are, and so on. And then the robot now has to approximate this too. So it has to estimate not just what the humans want to do, but also what humans expect the robot to be doing. This is what I'm calling M-hat-RH. And that actually, this second order model winds up being very helpful for the AI systems, the robots, embodied robots, or decision support systems, to either conform to the expectations humans have of them, or to explain their behavior if in fact it winds up winds up going away from the expectations that the humans have. And the explanations will essentially be changing MRH, by dialogue. So that's what in some sense explanations are. I want to show you some use cases of this in the work that we have done, and the two kinds of use cases that we look at are search and reconnaissance scenario, for example, in this particular is a toy version of search and reconnaissance scenario, and then which is a embodied robot. On the other side, we also do human AI interaction in the context of decision support systems. So, for example, a human mission planner getting help in completing their plans, a course of actions with the help of the AI system in the loop. Okay, so it turns out that the challenges are similar in both cases. Okay, let's get to what winds up happening in terms of conforming to expectations versus providing explanations. I pointed out that the robot now has the second order model of what the human thinks its model is, so MRH. And the robot's actual model, MR, might well differ from MRH. In most cases, humans may not have completely correct idea of what the robot's model is. So if they're exactly identical, it's a great world. In fact, the humans and robots will be able to work together quite fine. But most of the time, there would be differences. And in that case, as a consequence, the plans that are optimal for the robot may well be not seen as optimal according to the human's expectations of the robot. So that will lead to inexplicable behavior. So the humans are thinking, why is this robot doing this? You might not be surprised to hear that many, of the few robot factory accidents, many of them happen when unexpected behavior occurs because of, on the robot's part. And, many a time current robots are essentially fully controlled. And as we go forward, they'll become more autonomous. And so, in fact, the inexplicable behavior becomes a more important issue to control for. And in these cases, when there is this, robot realizes that MRH and MR are different, it has two options. One is conform to the expectations or change the MRH that the human has so that it's more closer to what the robot's actual model is. So the first one is what we call explicable planning, and the second one is providing explanations. And I want to show you some, demos of this to get a sense of this. So I'll be looking in this particular case at a, search and rescue kind of a scenario where a human commander is in a safe place and the robot is looking in some building, looking for injured people. Now, in the beginning, the human and the robot share the map of the environment, but then as the robot goes in, it has essentially more knowledge. For example, certain paths might be closed, certain paths that the human thought were actually feasible may not be feasible, and sometimes the paths might open too, okay? So in this particular case, it turns out that the shortest path to where the robot is supposed to go would have gone through this corridor, and it turns out there is an obstacle here. And the robot has two options here. One basically is to just essentially take time to remove the obstacle and go in the direction, in the path that the human expected it to go. And this is basically the robot showing explicable behavior. So you're conforming to the human's expectations. To do this computationally, essentially the robot has to take in its planning process, not only the cost of the current plan with respect to its model, but also how far this plan is from what the human is expecting it to do, and reduce that distance. So in some sense, it becomes a regularizer such that behaviors that are more in conformance with what humans expect the robot to do would be produced. Now, explicable planning is great. If you actually do what people expect you to do, you never have to open your mouth. But then your life can sometimes get quite hard because you're doing what people expect you to do rather than what is optimal for you. It's the same for people as well as for the robots. So conforming to expectations can be costly. So a second idea is the robot basically in this case saying, look, I'm not going to take that short path because that's closed. And so it's basically giving an explanation saying the path from P1 to P8 is not clear, and it's taking the second best path. So now the human basically not only is seeing that the robot is deviating from what they expected it, but they're getting this explanation. That explanation changes their model of the environment and model of the robot. With respect to that changed model, it turns out that the robot's behavior is indeed optimal. Okay, so here we are now talking about explanations as model reconciliation, and essentially the whole process of explanation is the robot trying to change the MRH of the humans with epsilon changes with respect to how the actions, the preconditions, the effects, and so on are different from what the human thinks they are, so that then the human would also be able to see that the robot's behavior is indeed optimal with respect to this changed model. Okay, so it turns out that searching for these explanations involves a model space search, and in this search you will be able to find a variety of different kinds of explanations, the minimal explanations as well as explanations that will stay the test of time in terms of longer sets of interactions. I do want you to understand that conciseness of explanations is important, because the robot can always just dump its own whole model onto the human and say, read this stuff. From this, you should be able to figure out what I'm doing. And that's just too hard for the humans to comprehend. And so you want to always provide explanations that make sense in that particular perspective. Okay, now, even though I talked about this as if explanations and explicability are two different phases, it turns out that they can be combined together. We have actually been working on this idea called expectation-aware planning, which takes both into account what the human expectations are and what the robot's goals are. And it also takes into account the robot's ontic actions, the actions that change the environment, and also communicative or explanatory actions, which essentially only change the human's mental model. And you can combine them, and this is a more complex planning process. In the old days, it's been called the epistemic planning. Typically, epistemic planning is actually quite costly, but in our scenario, for our kinds of scenarios, the two-level nesting, it turns out that we can compile this epistemic planning into single agent planning. Okay, so in this particular case, if it is a purely explicable plan, then the explanatory actions would not be there at all. Otherwise, there would be a combination of explanatory actions as well as ontic actions. And as I said, it can be compiled down into a single agent planning scenario, which gives you efficiency. And although I looked at robots because they make better demos, it turns out this can also be, the same ideas can be used in the context of decision support systems, and we have actually done that too. One other thing is that we basically can also wait for the human to express a question before providing explanations rather than directly providing explanations. And that is basically the idea of foil-based explanation. So you let the human ask a question, why not this other plan? And then the robot provides the explanation as to why the foil can be defeated. This particular foil-based explanation process can be sensitive to different levels of abstraction. And the very question that the human asks will allow the robot or the AI systems to localize where the human's model is. I want to also mention a little about the connection between this line of work and explainable AI in machine learning systems that some of you may have heard of. XAI has been hard, but mostly as a debugging tool for inscrutable representations by pointing parts of the model that, like, for example, this picture, this part is what makes me think it's a dog. This what makes me think it is a Alaskan Husky. And in fact, if you wind up pointing out a snow on the ground, then you realize that the system doesn't quite understand what the concept of Husky is. But pointing explanations are primitive. Explaining decisions will involve pointing over, explaining sequential decisions will involve pointing over space-time tubes. And in fact, civilization and symbolic reasoning emerged so that we can actually avoid doing that and exchange explanations in symbolic ways. Explanations are critical for collaboration, but they're not a soliloquy by the agent. And the kind of model reconciliation view we've been looking at fuse closely to psychological theories. Okay, and in fact, we also can show, in fact, some of the other work we have pointed out that keeping mental models of the humans and figuring out the kinds of classifications that they find, misclassifications they find particularly egregious versus misclassifications that are okay misclassifications, winds up improving the acceptance of machine learning systems. So not all failure modes are created equal. It's not just accuracy you should be counting. It is how egregious are your misclassifications. And you can do this as sort of connected to these mental modeling ideas. One thing that I want to mention is how does AI agent get the human's model? Sometimes you can start with the same beginning model, and then these models will be drifting, and so you will then, you can reason about the drifts. Other times you have to actually learn the model from either the traces, and we can also actually do this reasoning in a model-free way. For example, as I showed in the explicable planning, that distance between what the robot is doing and what the humans expect it to do, and the distance you want to minimize, instead of directly computing that distance from explicit models, I can compute this indirectly by learning a sort of a preference function, a labeling function from the humans, and using that labeling function in place of the explicit model. So this is a way in which you are actually using the model in a model-free way in this human AI interaction. It turns out that the same idea can be extended even when you have explanations involved, explanatory actions involved, because you can actually do the same sort of labeling computation, labeling function learning, except this time you would be doing your behavior as well as some explanatory messages thrown in, and then see whether how the labeling from the human changes. So in some sense, you are indirectly learning the semantics of the explanatory messages themselves. We can also look at differing vocabularies, and when there is vocabulary differences, basically the machine has to convert its explanation into concepts that humans can understand. And so when basically you will learn concept classifiers and convert the explanations in terms of these concepts, and there is some work that we are currently involved in on that too. And then finally, from the point of view of checking whether these kinds of ideas make sense, for humans, you do actually need to do careful, systematic human subject studies. And we have done that. We have actually collaborated, and I would suggest that anybody interested in human AI system should be looking very seriously at careful human subject studies. And so we do that, and we, for example, have shown that the kind of model of reconciliation explanations and explicable behavior do help the support the interaction between the machines and the human and AI systems. There are a variety of extensions of what we have shown you. A few things that I'll mention is basically include allowing for customized expressions for multiple humans in the loop. In this particular case, there are multiple humans, and the system essentially will track the model separately and provide explanations to them separately. And so that's sort of context-specific explanations. We've also been looking at how to generalize these notions of interpretability from both our work as well as from other communities, including robotics community, and to talk about landscape of definitions for interpretable behavior, and also providing a Bayesian account of this whole interpretable behavior. Now, I've been talking about how to use these mental models in the context of supporting humans, but you can also, in a cooperative setting, you can also use the same ideas. Once you are tracking mental models, you can use that to deceive them too. So for example, in this particular demo, a robot in one case using the partial observability is making Anaga do something else so that she won't be able to see the action it is doing. And in the other case, she's asking her attention directly to look at what she's doing. So in this particular way, you can simultaneously signal to your friends and head fake enemies. This is also a direction that we will be able to use using the mental modeling. That leads us to almost my last part, which is that there are a bunch of ethical quandaries that this mental modeling of humans bring into play. Evolutionarily, mental modeling allowed us both to cooperate or compete. Lying becomes possible. If you go back to Salian test, lying becomes possible only because we can model others' mental states and realize they're different from ours. Human-aware AI systems with mental modeling capabilities bring many additional ethical quandaries, such as would we want AI systems, AI assistant tell us white lies, for example. And then also, when humans are working with systems that have social intelligence, they tend to fall a lot more harder for potential manipulation by those systems. So these are things that you need to worry about. As I said, head fakes are really the most powerful deep fakes, and we need to be worried about those kinds of social issues. We have actually shown that the model reconciliation framework can be used to capture both lies of omission and lies of commission. And we have done some work that we published in the AI Ethics and Society Conference on how, to what extent are people willing to be told white lies by AI systems as against other humans. You do realize that human society works on us telling each other some white lies. For example, if you ask me, how do you look? I know that I'm supposed to say you look good. Right? So there are some white lies we do. The question is, do you want AI systems to tell white lies to kind of induce right kind of behavior on people, and nudging and so on? So these are very interesting challenges that come in. In summary, effective human interaction requires, of course, AI systems to be able to manage human mental models. I showed you some of the technical aspects as well as the challenges about explicable behavior, explanation generation, and handling vocabulary differences. And then I told you that we need to actually have human subject studies carefully to check whether our theories make sense. And then mental modeling capabilities open up a new Pandora's box of ethical issues. You do need to mental model to effectively cooperate, but then that also allows for head fakes, and we need to think about how to manage them. There is a paper on some of these things in the most recent AI magazine as the cover article that you might be interested in looking at. And I want to end on this note. It looks as if getting computers to work with humans and be aware of AI systems, to be aware of humans, brings in a whole new slew of additional challenges. And you might wonder, why do I want to do that? Well, on the other hand, as you know, basically most of you want the AI systems to actually work within the society we have, rather than us humans going into the society of robots. And so it is a worthwhile thing for us to take human-aware AI systems and their challenges seriously. In the introduction to AI courses, people talk about intelligent agents, and an intelligent agent basically doesn't model much in the normal architecture. It doesn't model much the other human agents in the environment. And I think increasingly, we need to consider intelligent agent architectures that will take both the human mental states, the effects of the agent's actions on the human mental states as well as the environment. And that's when we will have truly human-aware AI systems. I'm going to stop here with that summary slide, and I'll take any questions you might have. Thank you.
Well, thank you very much, Professor Shibaro Kambambati, for your wonderful presentation. And in his session, Professor Kambambati has introduced to us AI systems which are aware of humans and so behave in ways that humans can understand. And he said that in order to have effective human-AI collaboration, we essentially need AI systems that can take into account the assumption models that humans expect, and that these kinds of AI systems will be able to behave or be explained in ways that humans understand. And as he mentioned in his presentation, Q&A session regarding Professor Kamabati's presentation will take place after the fourth session, so please take a note of it. Well, for today's final technology session, we have the robotics sessions. Daniel Lee from Cornell Tech, who is the Corporate Executive Vice President of Samsung Electronics, will be presenting for us, and will be informed on AI or for robots and people. Professor Lee is a fellow of IEEE and AAAI and professor at Cornell Tech. Not only that, he is serving as the head of Samsung AI Center in New York since 2018. His main research area is robotics, and he is actively searching for ways to apply the principle that work in biological principle to intelligent robots. So, without further ado, let's have the presentation.
Thank you for that introduction. My name is Dan Lee, and it's my pleasure to join you at the Samsung AI Forum today, albeit virtually. I think you've heard a lot of interesting talks about artificial intelligence, and it's my pleasure to share my perspective on AI and its future impact and current work on robotics. So let's begin. The main motivation of my work is to try to understand the difference between artificial intelligence and natural intelligence. This goes back to the beginning of my research career 30 years ago when I started working as a postdoc with Sebastian Sung at Bell Labs. At that time, we were very interested in trying to understand neural models of brain mechanisms and to try to understand how those neural models could be used to explain behaviors in various types of animals. In the same way, we want to try to build computers and computing devices that can replicate some of those kinds of thinking processes going on in biology. And we like to understand the fundamental limits and challenges of trying to see about how we can build AI systems that can approach or maybe even surpass the performance of biological systems. And that's really the fundamental question that I'd like to try to address is what are some of the limitations? What are some of the remaining challenges in trying to build AI systems that can approach the performance levels of what we expect in animals and in humans? So let's think about how we can measure these differences. So one way we measure these differences between AI and human performance is to do man versus machine contests. And this has been happening for a number of years. You know, we've started back in the 90s with looking at how we can make computers play chess, the game of chess. More recently, we've had computers playing things like trivia games. And of course, the excitement back in 2016, where DeepMind built AlphaGo that beat Isidol in Go. And in all these systems, what we've seen is a steady progression of being able to build computers and algorithms that can outperform humans, the world's best humans, in these particular domains. So this, of course, has led to this big, exciting time in artificial intelligence research. And the question is, what are the limitations of the current approaches? Now, what we've seen then is that with these approaches where we have good performance is in these kind of virtual worlds, right? When we think about Go, we have a particular board game that has well-defined rules, well-defined configurations, and all the players know exactly kind of what the configuration of the board is and what happens when they place a particular piece in a certain location. Similarly, we've seen successes in AI in things like playing video games, where again, the kind of rules are very well known. The images that you're getting from the screen are quite well defined. And the computers then are able to understand with a lot of data, are able to understand kind of all the various dynamics and transitions that occur in these virtual worlds. And this has really been the domain of success for AI systems today, is in environments where kind of the inputs are quite well defined. We know kind of how the transitions between the different states of the world occur, and what the rules of the world are. However, we've had less success in AI when we deal with our messy physical world, right? And the reason for this is that the real physical world is much more complex than something like a video game, right? When we actually step out into the real world, we don't know quite what will happen when we step on that piece of ground, right? We don't have a good model sometimes of what happens if that ground is sandy, or maybe that ground has some ice on it, or it's stony, rocky. I mean, all these things will dramatically change what will happen if we try to take, say, a running step on that piece of ground. In the same way, we don't know the configurations of all the various objects that are happening in the world around us, especially objects that are not well defined, that are flexible and deformable and kind of can slide and can kind of move with different types of precision. And of course, we don't know the dynamics, right? This is really trying to understand all of physics in the world by building these models, and it's really hard to do from kind of prior knowledge to build these types of systems. And this is what makes kind of AI successful in the real physical world much more difficult and challenging to do than building AI systems that can succeed in virtual environments. And so this is really, I think, the domain that we would like to try to work with, is to try to have AI that can actually understand and respond and do things in the real physical world. So this is what I see as a next frontier for AI, is to build, computing devices and systems that handle the challenges of dealing with the uncertainties, the uncertain dynamics in the physical world, the kind of partial observability that you can't see everything at once, the how other agents in the world will act, and then being able to adapt and respond in real time to changing events in this kind of ever-changing worlds and in our world. So this is what I think is really the next frontier for AI, is really to build these robots, machines that can kind of respond to these challenges. And this has been a pipe dream for science fiction for many, many years, right? We've seen numerous robots that are in the movies that can handle these challenges, but we still don't have them in our houses or, in our daily lives. And this, I think, is really then where the next frontier of research will hopefully develop our ability to build machines that can actually do some of these dream-like behaviors that we're seeing in the movies. Okay? And this is why, as a next frontier for AI, to be able to marry AI intelligence with these electromechanical devices is really the next challenge. And this is why what we've done is actually at Samsung, we've started an AI center in New York, which I've had the pleasure of being at for the last 2 years. And what we're doing there is we're focusing on building technologies, doing research, and building these machines, these robots that can handle and intelligently understand and react to events in the real world, in the physical environment. Okay? And so how do we approach this problem? It's a very, very complex, complicated problem. And the way we break down this research, this problem, into various stages, right? So when we want to build a machine, or when as animals and biological machines want to try to understand the world, the first step of this process is perception. That is, we need to take in information about the surrounding world from our senses, whether that's, vision, hearing, smell, touch, other senses, and to be able to take that information in and to make some sort of model or understanding of the surrounding environment. This is what we call the world model. And then from this world model, what we need to do is then to make some sort of decisions and make some plans. Right? Given the current state of the world around us, what should we do next? Then what should we do, kind of a minute from now? What should we be doing an hour from now? What should we be doing a year from now? These are the types of things that we need to do with our understanding of the world. We need also make these kind of intelligent plans. And then once we are able to build these plans, we need to act on them. We actually need to, carry out these plans. So then, of course, then it's a matter of, physically being able to do the types of things that we would like, our systems to be able to perform so that they can actually change the world in some sort of a useful manner. And this is the way that we break down the problem in robot intelligence. We need robots that can intelligently perceive the world, that can make decisions and plan things in the world, and then to actually act in the world, and then to be able to complete this loop in kind of a real-time setting. That is, none of these things should take a large amount of time. Otherwise, by the time the robots figure out what to do, the world has already changed. So these are the challenging problems that we're trying to address. And what I wanted to do today is to share some of the methodologies and technologies that we've developed to try to address each of these different areas of robot intelligence. So let's first talk about the problem of robot perception. Okay, and what we mean by perception is taking in, again, information from our raw sensor signals, that is the cameras or the microphones or the tactile sensors, about the world around us, and then to be able to build kind of what we call the state, to estimate the state of the world around. That is, whether that's the three-dimensional structure of the world in geometry, or the presence and identification of different agents in the environment, or to try to identify even their intentions in the environment. This is the idea of going from raw sensor signals to estimating the world state. And a critical part of this in robot intelligence is to be able to do this very robustly, to map input sensor signals to these efficient world state representations that then the robots can reason about to make intelligent decisions for. All right, so that's the first stage of how we break down the AI problem for robotics. So let me give you an example of some of the types of research that we're doing at the Samsung AI Center. So one sensor that we've been playing around with is something called a dynamic vision sensor. And this is a device that Samsung has built that basically is a new type of camera. And the way this camera works is very different from your conventional camera. A conventional camera, when it takes a picture, what it does is it has a bunch of pixels, and then it opens a shutter, and then in this shutter, it opens it for a fixed amount of time, typically, say on the order of 30 milliseconds. And then what it tries to then do is then to take that information and basically to integrate the number of photons in those pixels, and then builds a pixel representation of the world that's related to the intensity of light that it's actually integrated in that window of time. Now, what the dynamic vision sensor does is it actually images the world much more like what our human eye retina does, right? It takes in light intensity and only looks for changes in the light intensity. And then when things change, it emits a spike, a signal that indicates then that this particular pixel has actually increased or decreased in intensity. And this is a much more compact representation of the world in the sense that if the world doesn't change, then this new sensor does not have to actually output anything, and the rest of your system then will know that the world has not changed, and therefore it should maybe still continue doing what it's been previously decided to do. So what we have here is we have the sensor that outputs these spikes that represents changes in the environment. And what we then need to do for perception is figure out how to efficiently process the set of spikes coming from this DVS camera, and then to be able to, say, recognize other objects in the environment and to estimate different properties of things happening in the world around it. So we've developed a system that can take in these input spikes from the DVS sensor, process them, reducing the complexity of that information, and then to take that information and feed that ultimately into a binary neural network that can segment and detect the various objects in the input stream. This is then the method that we use to process the sensor information coming from the DVS to represent the state of the world around it. And so this is kind of a new technology that allows us to very quickly use camera information in this new way that's then able to infer what's happening in the world around it, around the robot, without having to do kind of much more complex visual processing. So that's an example of this perception problem using this kind of novel dynamic vision sensor. Now, another technology that we've developed in the machine learning community here is to actually think about how we can do this kind of perception using what we call a higher order function neural network. And here the basic idea is the following, right? When we do perceptual processing, you typically think about using some sort of maybe neural network that takes in the input signal and then outputs, this world state representation. But in our case, the way we think about the world, that is the state of the world, we can represent as a second neural network. Okay, so the way this higher order function network works is that when the input signal comes into the higher order neural network, that gets processed, and then the output of this neural network is a set of weights, the weights of which represent another neural network, which then represents the world state. So for instance, you could have, say an input image of this plane from one perspective. The output of this higher order neural network will be then a set of weights. And what this set of weights represents is another neural network that maps points in three-dimensional space onto the surface of the plane's object kind of envelope, so the three-dimensional structure of this plane. So that's the idea, is that we can use this kind of dual model of neural networks to represent the perception as well as the state of the world using this kind of technology. And the applications of this method are numerous. So as I showed you, one application of this would be to take in, say, images of the world, and then to output the kind of three-dimensional point cloud of the different objects. And this is one aspect of using the higher order function, is to kind of generate these point clouds. We've also shown how instead of point clouds, you could actually directly output the surface patches of the object. So to get kind of more information about the three-dimensional nature of these objects and to be able to render them for, say, graphics purposes, we have another higher order function neural network that can do this. And so we can see that the kind of efficiency of having this type of representation for the state of the object is very good. And what we can then see is that we can do some quantitative experiments to measure the performance of how well these neural networks work, these higher order function neural networks work. And this is showing some results on a standard data set called ShapeNet, where given input images of these different objects, the higher order function network represents the state of the object in terms of these, say, point clouds. And then we can measure how close the the point cloud outputted by this neural network is compared to the ground truth model of that object. And what we can see is that these methods are very competitive and also much more compact representation compared to other state-of-the-art methods for doing this kind of point cloud estimation. So that's another example of being able to use kind of neural network, machine learning to kind of build very efficient representations of world models directly from sensor data. Now let's talk about the next stage, right? The planning. And here, if the robot has some sort of view or model of what's happening in the world around it, it still needs to decide what to do. And the way we think about this problem is, we want to plan out, let's say, a trajectory for the robot. Like, where should the robot move in terms of all its different, joints and its legs and arms or whatever degrees of freedom that it has. And so the way we represent this is that from our world model, what we get is we get our initial kind of pose configuration of our robot. That's our initial state. Then we make a decision about where the robot should go. That's the final state. And then what we like to try to do is to try to figure out the optimal trajectory to go from our kind of current state to our desired state through what we call configuration space. That is kind of the space of all possible configurations of the robot. And what we then do is we can define a cost function. That is, some places to go are bad and some places to go are very good. And so, some places have high cost and some places have low cost. What we can then do is write down an optimization problem that minimizes something like the integrated cost over a trajectory. And then what we need to do is find out the optimal trajectory that connects the initial state with the final state. And one kind of typical computational way of trying to solve this problem is to take the configuration space and discretize it, turn it into a graph of some sort. And then what you have is then you have an optimal path planning problem on a graph. That is, which set of nodes to go through in this graph to get from the initial state to the final state with the minimum cost. And that's the kind of conventional way that we think about planning problems in robotics, is to optimize these trajectories by doing this kind of approach. But typically, these things break down when the robots get more complicated or the environments get more complicated. That is, the kind of optimization over these trajectories becomes a much harder problem. And then the time it takes to actually solve these optimization algorithms is too long for the robot to respond reliably. And so what we like to do is think about new methods using machine learning to basically speed up this planning for robotic intelligence. And so here's an example where what we've done is we've taken a traditional kind of planner that I described to you, where we discretize state space. We do this planning in this on this graph in state space. This is called a RRT algorithm. We then generate a trajectory, this optimal trajectory. And then what we try to do is we try to train a neural network again that will mimic the kind of trajectories output by this conventional planner used in robotics. And what we found then is by mimicking the kind of conventional planners, we can still do very well in performance on of generating these trajectories, but then we also have the advantage of being able to do this very, very quickly and robustly in a lot of new environments. Now, another way to approach a robotic planning problem is that we can actually have a neural network, instead of trying to generate a trajectory directly, we could actually have the neural network, according to this kind of higher order function neural network, generate what we call the value function or the cost to go function in this configuration space. And what happens then is that we actually have a small neural network that can be used to map out essentially all the different locations in this configuration space. And then the optimal trajectory is found by just doing simple gradient descent on this learned value function to figure out kind of which direction to flow in this configuration space to generate the optimal trajectory. So this is another example of recent work where we're leveraging, machine learning to be able to efficiently figure out how to represent the value function of these more complicated robotic systems, and then be able to use that to be able to control and to generate these trajectories for the robots. Okay. So then the applications of these methods is then to actually do something with the robot, right? Now we're talking about action. So the example I showed you where we learned, this how to plan the trajectories for a robot. Here we're showing an application of this, of having a robot arm using a very simple tool to pick up a set of objects. In this case, it's a set of shoes. And what the robot has done is that on these shoes, it's never seen these shoes before. It's actually learned how to generalize, how to pick up, from its training set of shoes to be able to then figure out very quickly that with these new set of shoes, how to actually, hook them in the right place so that it's able to generate the appropriate trajectories to kind of pick them up in a very rapid way. So that is the kind of idea, is an application of some of these technologies to be able to generalize and use them very efficiently on, say, some novel objects. Here's another example of a robot action control system that we've been working on at Samsung. Here, the idea is actually using a novel sensor now. In this case, it's a tactile sensor. And here, the idea is to actually have the robot learn how to take the information, the state information coming from the sensor, and then to kind of control the gripping force of the robot arm so that it can actually smoothly slide, say, this object in its hand to, say, reposition the object when it needs to. And this is, of course, an example of what we call dexterous manipulation, that, in one hand, this robot is able to reposition and slide objects. And what we're seeing now is then the ability to try to generalize to new objects and to be able to slide these different objects depending upon the environment and situation and what it needs to do. Okay. And finally, some of the things that we think about with these robot intelligence is the need for the robots to also interact with humans, right? So if you have a robot that's actually doing something on its own and you have a human in the environment, of course, we want to think about how to have safe and reliable interactions between what the human wants to do and what the robot is planning to do. And so what we have is we also have some research looking at how we can actually integrate the kind of world representations coming from the robot and trying to figure out how we can have it perform these actions in a smooth and safe way that will then assist what a human user would like the robot to do. And this is, of course, is an interesting idea of how we can then have better synergy between human users and the kinds of autonomous robot technologies that we're trying to build. Yeah. So what we then try to like to do in general is to make AI so that it can actually improve your daily life, not just your virtual life, but your daily life. That is, can we build autonomous systems, robots, that can understand the complexities of our environments that we live in, understand those complexities, and then actually be able to respond to them in intelligent ways so that they can help us with the tasks that we have to do on an everyday basis. And these are the types of things that we're excited to do and develop, is to build the fundamental research and technologies that will enable future products that will really make an impact in our daily life. Now, this is still a research problem, because if you look at kind of how far we are from a comparison to how well humans perform some of these tasks, we're still a long ways away, as opposed to something like playing Go or a video game. We see that our robotic technology compared to what humans can do, and this is an example of a boy that's able to stack a number of cups using vision sensors, tactile sensors, being able to plan out the trajectories of his hands, figuring out kind of when the cups are stacked in the right position in place, and then being able to respond to slight perturbations in the environment. We see that the amazing ability of a human to do this is still very far from what our current technology can do. And this, of course, is what makes research exciting, is that we have this challenging problem. What we like to now do is think about novel methods and technologies that will start to approach building systems that can achieve this type of level of performance over time. And this is, of course, where we would like to get to someday. So finally, I would like to acknowledge my colleagues at the Samsung AI Center in New York. There's a picture of the researchers and staff there at the center. We're working on these challenging problems, but they're doing amazing work, making amazing progress in the couple of years that we've been working on these tasks. And what we like to be able to do is to try to leverage this to try to really make an impact in your future lives. So if you're interested in more details, I didn't have enough time here today to kind of get into all the details. We have a number of papers that have been published. Here's a list of some of the papers I described using kind of robotic perception. And then we also have some papers that describe how we can do some of these manipulation tasks. And this is the output of our research. And I'm very excited that we're able to continue this work, and that we will be able to kind of hopefully make future progress. And of course, I'd love to maybe see you someday helping us out in this endeavor. Thank you very much for your attention.
Thank you very much, Daniel Lee, for your wonderful presentation. And today's lecture, Dr. Lee has shared his recent work on robot intelligence, saying that AI is very successful in the virtual world, where all the rules and configurations are well defined, but not so much in the real world, which is much more complex, and that in order for AI to understand the world, which is to respond appropriately, we need to explore a new field in AI, which is robot intelligence, a combination of AI and robotics. So now we'll connect with Professor Shubhara Kamabati and Daniel Lee to proceed the Q&A session. And Sebastian Singh will again be leading the talk.
Hi, everyone. Shubhara, I'd like to just start by asking some questions to clarify in my own mind what you're doing. So the first question is, so it's really a very fascinating question, how robots can understand or model the human mind. I'm curious why you target the robot understanding the human predicting the robot, as opposed to just the robot predicting what the human's going to do. Because that also may require a mental model. For example, in autonomous driving, if I'm an autonomous car, Knowing what the human is looking at may help me predict what the informational state is, may help me predict what that human's going to do. So why do you make it even more complicated by asking, can the human predict what I'm going to do? Why go straight to that as opposed to the first problem? Sorry, we're not hearing.
Okay. Yeah.
Okay, great. We can hear you now.
Can you hear me now? I'm sorry. The research in intention recognition and projection has been going on for much longer time. And I mentioned it in passing in the beginning. My point is that to actually understand whether what robot is doing, what AI systems are doing is interpretable to the human or not, you have to consider this second order model. That's pretty much what determines both explicable behavior, is the AI system behaving the way you're expecting it to behave, and also if it doesn't, then what does explanation supposed to contain? So I'm not saying that other part is not needed. I'm just saying this part is essentially what you need to deal with if you have to consider interpretability. In the first case, the robot is sort of trying to anticipate what human is doing. Here, you are actually making sure that it's also realizing what the human expects it to do, and that's what is interpretable to some extent.
You also had an anecdote saying that many accidents with robots happen because humans can't predict what the robot's going to do. Well, you didn't have the anecdote. You just referred to it. So can you give us some anecdotes? Is that really the case? What kind of accidents?
So I think in factories, I mean, I guess you guys know a lot more about this, but in factories in general, we right now still have robots in cages because we can't completely figure out what they would be doing. And so the only way to ensure safety is to have robots in cages. So once you have actually freely moving robots, then it becomes a lot more important to be able to figure out that they're actually acting in the ways humans expect. And some of the even in-cage accidents have been finally got down to the robot behaving in unexpected ways, where unexpected here is that the humans didn't expect it to behave that way. So that indeed becomes a big issue, in terms of human safety.
Now, this kind of problem of what do I think that you think that I think that you think that I think, that's you're sort of getting towards that, and the formalization of that's best known is that of game theory. So this is actually a question that was on the site. So what's the relation of what you're doing to game theory, and should the Nash equilibrium be used to understand these mental models?
So first of all, two parts to the answer. So first of all, it's actually infinite regress in mental modeling is thankfully, while it is theoretically required, in practice, it's been sort of, psychologists have studied this and said, people tend to go about 2.1 levels on the average. That's about it. And so if you go around 2, then you already have the kind of human level social interaction. There's probably not a very complex maneuvering going on, but certainly human level social interaction can occur, if you go 2 levels. In terms of the game theoretic aspects, as I answered that question just now, I think is, in general, once you start talking about this, much of what I've shown here is taking one snapshot, what happens in a single snapshot. But humans and robots, AI systems will work together over longer periods of time. And it brings in all sorts of interesting game theoretic considerations. In fact, I just put in a paper there, linked in that question, where we actually look at a situation where the robot might decide to engender trust in the beginning behaviors in the human. And then once the humans actually trust the robot, then they don't get as affected by unsurprising behavior. We do this with people that we know. For people that we don't know, if they do something that we didn't expect, we get kind of mad. But people that we know, we kind of realize that maybe they had a good reason, we'll give them the benefit of doubt. And this is something that humans do all the time. And so this can be used to sort of reduce the computational cost of being, being explicable to the human in a longer term scenario. And those sorts of things will be posed indeed as game theoretic considerations.
Great. So I'd like to ask some questions to Dan now. Dan, you talked about the DVS as a novel sensor that's helpful in perception. And somebody asked on the site, in general, how much progress can we make by using new sensors in robotics, more generally?
Sure, I think it's a great question is how, say, biologically inspired should we be with our sensors? I think the main question is how much information and how kind of real-time information can we get from these sensors and the power requirements for specific applications. So something like the DVS is very nice because it has, it could be very much low power. It doesn't have that much communication bandwidth compared to regular cameras. And so those make it attractive to actually implement, say, in mobile robotics, for instance, or for high-speed vision systems or other types of applications. So definitely sensors help, but that's not the end all and be all for intelligence. The rest of the pipeline that, I talked about in terms of, processing, turning into state estimation, understanding the world, and then being able to react to the world, those are still the challenging problems. Even if you had, new sensors, you would still have to solve the rest of the problem.
Great. And now here's a big picture question. So you talked about an amazing array of researches. But I guess I'm curious about the big picture in which those projects fit. Can you maybe contrast your approach with other approaches, general approaches that are being used in manipulation? For example, doing everything in simulation and then going sim to real, or having a large number of robot arms and using reinforcement learning to pull experiences across those arms. How do you see your research being similar or different to the other kinds of approaches?
No, great kind of a question about what paradigm to use to solve this kind of unsolved problem. And right now, what you're seeing is one approach is to kind of use the tools that we know how to do today and just scale it up and see if, scale works, right? Like just throwing new data at it, trying to do it in simulation by having, lots and lots of computers simulate the process. The question, though, is that will it actually be enough to handle the real world? The real world is very complicated. We have something called the simulation to reality gap, which means that none of our simulators today can really mimic what happens in reality. And so something that you learn in simulation doesn't really carry over to a real physical robot. And so the question is, can we just scale up what we're currently doing in AI, or do we need new paradigms to think about new ways of doing the representations and to make more efficient learning algorithms to handle this what I consider a much more complex problem to have robots really interact in the real physical world. So yeah, I think it remains to be seen kind of which way is the best way and will ultimately solve this problem. But I always like to think that human intelligence should be part of the solution as well.
But is there a simple way to understand how your approach is different from some of these other approaches? Is there like a simple way to sum it up?
Well, I think we are using some knowledge of the process in terms of how we break down the problem, and then we are thinking about the correct representations at the different stages of the robotic pipeline, and then trying to build that in to some extent into the kinds of neural networks that we use to help more efficiently learn and be able to generalize better with a limited amount of data. And that, I think, is the key challenge is humans are very good at just going into an environment and within kind of one trial being able to kind of adapt to it. And that's what we need our robots to be able to do, rather than have to use lots and lots of samples and trials to even figure out how to take the first step.
And the separation into the different modules for perception, planning and action. So that is kind of a classical separation in robotics, and some people have argued that you need to break down those barriers. So what's your opinion on that?
I mean, I agree that we should break down some of these barriers, but I don't think we should throw away the kind of notions and the ways we think about, well, what happens to representations at these different levels. So some of our work does break down some of the barriers between, say, perception and planning, or planning and control. There is an approach called end-to-end learning, which is to say we're just going to do everything kind of tabula rasa, from pixels of cameras to actual joint torques on the motors. And what happens then is that then you really need lots and lots of training samples and experience, and even for the robot to even learn how to take the first step. And so this is why I think if you want to make a practical impact, you have to think about some of the issues in terms of how things are represented and what kinds of models make sense and how to actually learn efficiently with a limited amount of data.
Well, great. Thanks a lot, Dan and Subaru. I think we can say that this Q&A for this session, we've wrapped it up with some stimulating discussions.
Yes.
It's time to move on.
Okay, right. Well, thank you very much for the explanations. We have very much benefited from the presentations for our speakers. As we wrap up all our session and the Q&A, we'll now proceed with the panel discussions, and we're going to have more talk and detail. So we have invited the speakers of our first two sessions, session 1 and 2, and we guarantee that it will be a very meaningful time as we discuss over various topics. So please stay tuned until the end. So I think our speakers are now online, so please welcome them. First, the first panelist, we have Professor Christopher Manning of Stanford University. Hello. Thank you very much for joining us. Yeah, thank you. Well, next to him, we have Professor Debbie Park of Georgia Institute of Technology, who spoke for the Vision session. Good to see you back. Hello.
Hi everyone.
Thank you. And we have Professor Subaru Kambambati of Arizona State University. Thank you. Finally, we have Daniel Lee, Corporate Executive Vice President of Samsung Electronics. And our President, Seung, will now lead this session as well. Please.
Hi, everyone. I'd like to lob the first question at Subaru. He made a provocative statement, which is that head fakes are the most dangerous, more dangerous than deep fakes. And I'm curious whether he could elaborate on that claim.
So I don't know if you have seen this old movie called Sting. If you haven't, you should. It's the Robert Redford, Paul Newman movie. The entire movie is a sting, which essentially plays with your belief system, and at the end, essentially they will get their way. I actually think of deep fakes as essentially the perceptual version of the head fake. And what you really can do, if you can manipulate people's beliefs, you can do a lot more than just showing them pictures. And so that's really what I have in mind. And in fact, and as we actually start talking about the ability to reason with mental models, which is required for cooperation, we also open the Pandora's box of being able to use it for manipulation. And I think this came up in all the talks, and that's one of the reasons I think it's great that AI people have to be very careful about, what are the Pandora's box has to be opened, because in fact there are useful capabilities we get, but we should be very much careful about the misuses that these things can be put to. So in fact, the model reconciliation stuff that I talked about, is already can tell you the lies that you are likely to believe. And we did actually a study checking whether people would mind being told white lies if they think it is a human telling them the white lie versus if they think it's an AI system telling them the white lie. And the lie is actually being generated by the AI system in this particular case. And there's fascinating issues that come up in terms of once you start looking at mental models. I joke that I was ecstatic when my son told his first lie because I knew he had a working brain. He knew that he not only knows his beliefs, he knew that his beliefs are different from my beliefs and he can play with them, and he hasn't ever looked back after that. And that's really what human intelligence is. We are not reducing our capabilities. Integrity is knowing that you can cheat and choosing not to. So all of these things are basically connected. In my mind, that head fakes really are mental model manipulations, and deep fakes are just one particular part of it, which is perceptual. And we can talk a lot separately about how AI currently separates perception from the system one from system two, and perception from mental tasks. We need to obviously bring them together. That's like a huge challenge for AI to do.
Hey, I'd like to make this free form, so if any of our speakers who are outspoken and brilliant people, if they want to chime in here, they should just feel free to go ahead. I'll moderate if it gets too hot. So, okay. Anyone want to follow up on that?
I'll make a comment. Yeah, so obviously this isn't only an AI problem, because I mean, there's been a lot of attention in recent years how social media, or in general, a lot of websites in general, work to manipulate people. I mean, initially, a lot of their interest is in manipulating people to keep their engagement on platforms, but it turns out that often one of the most effective ways of doing that is to manipulate their beliefs. And so it's very much a problem of our modern tech society that precedes really the use of AI to do it. But there's no doubt at all that we should be very worried, because it seems like there's good reason to think that you can do it even more effectively with the emerging AI methods.
So, if I might add, before deepfakes, we had photoshopping, but people had to make the fakes. The worry about it is now you don't even need these poorly paid Russian people or whatever making these things. You can just have AI systems do it. It's the same thing with now social media. There are some people who are actually kind of playing with your belief system. Imagine when you have essentially that sort of thing is automated. That is a pretty worrisome problem. So to me, that's exactly. I mean, deepfakes were there before. It's just it took a long time to generate a good deepfake. Now, you can mass produce them. Anybody can go to, whatever, like, zombifyme.com and then become a zombie, for example, just for the Halloween and so on and so forth. And so we are opening this. We are basically, as Devi was talking about, it opens up all sorts of beautiful creative possibilities. I tend to think of the fact that all of entertainment is willful suspension of disbelief. We know that it's not happening on the movie, but there is a point where they have to make it look as if it's really happening, and we are doing that, and so AI systems being able to do that is amazing.
That's right.
But on the other hand, it get you lots of problems too.
Your news story about AI helps women cross the street, I really wanted to believe that. I suspended my disbelief. I wanted to believe it because it was such a wonderful story.
That's the reason I put it there, because for some reason I think AI killing lots of people will be in the New York Times front page, but not that, unfortunately.
I have to say, I very much more prefer Devi's music fake animations to Sebastian, you becoming Mona Lisa in terms of creativity.
Yeah, and I think going back to the sort of human-machine interaction and trust and all of that, actually Rao had given this one example many years ago that stuck with me, that apparently there are these studies that if cab drivers are chatty, then the passenger tends to trust the driver more. And so the question is, if a cab driver is chit-chatting for that purpose, is that manipulation or not? And I don't know if there are clear answers to that and how that feeds into sort of human-machine interaction and interpretability and trying to gain trust and things of that sort. Yeah.
Well, Chris talked about that in his chatbot research, just having the chatbot volunteer anecdotes, right?
Yeah.
So did you feel any moral qualms about that as being manipulative? Just putting you on the spot, Chris.
Yeah, I mean, it's actually something we thought and talked about and did things to mitigate. I mean, I think we weren't worried just at the level of chattiness. I think our whole goal was to provide something that was chatty and tried to have something of a relationship. And, people were choosing to engage, to spend time with our chatbot. But, I mean, there are very many ways in which a chatbot can do harm. And I mean, obviously, if you're a malicious actor, you can absolutely be designing a manipulative chatbot that's trying to do harm. But, even if you're nice, good-minded people like us, I mean, you can easily mess up, right? If the person on the end is saying something sensitive and revealing, and, quite often our natural language understanding didn't really understand it that well, and we just say something uncaring or completely inappropriate in response, I mean, that's not helping the world or the person on the other end. And so, we certainly tried to do things like that. It's a very hard problem to solve in general, because the whole problem is we don't have full understanding of language nor of human society. That's why we need the common sense knowledge as well. So, really what we were able to do was sort of a mishmash of strategies to try and minimize that, taking care in what kinds of data we use to train the models. We didn't train it from places like Reddit, which aren't often very pleasant conversations. Then doing other things of sort of then trying to, frankly, we just avoided topics that we thought were too sensitive because it seemed too dangerous to go some places, but then also using classifiers to post-filter what was generated to try and make sure that we weren't doing anything problematic. But, I just wouldn't want to claim that we had anything foolproof. We didn't.
I mean, it's well known that in advertising, that if you provide, or marketing, if you provide anecdotes about a product, it makes people trust it more. This wine was made from grapes that were, my grandmother walked all over them to stamp them out in 1954 or something like that. So it's well known that irrelevant information and anecdotes it's a manipulative kind of thing in marketing and advertising. So we're just, in some sense, as Subarao said, AI is sort of scaling up the ability for people to manipulate in well-known ways.
I think it's important to remember that, at the time of Joe Weizenbaum and his ELIZA chatbot, which looks obviously so old-fashioned, people were pouring their hearts out for this pattern recognition system. Humans have this crazy anthropomorphization tendency. And so already they're just going to suspend their disbelief and think that they are, seeing Mother Mary on, burnt toast, or they're talking to a real Rogerian psychologist on a pattern recognition system. And so now we are actually coming into the mix, and we are trying to do slightly more goal-directed conversations. Obviously we should be very worried about the manipulation aspects, to some extent. But again, I think even just trying to do what you expect me to do when it is actually costly to me, which I made it sound as if it's a good thing for AI systems to do, you can argue that that is in itself a manipulation. If it is hard for you to do this, you should have told me this, as against just doing what I expect you to do. So there are actually mythological stories about this sort of thing. Devi will know, for example, Parshurama's story. And, these are all these beautiful things that humans have. And, I guess we improve the interaction by doing this, but there is always this worry as to, A, is it manipulation, and B, is it deliberate manipulation? And that becomes a lot more interesting issue. So right now, thankfully, at least AI systems are doing kind of inadvertent manipulations because we are not that good yet for mental fakes, but, when they're actually really able to do good manipulation, it's because there's a human in the loop along with the deepfake system on the other side. But, we should be worried about the slightly further future where, in fact, there is no person needed. And then, there's just high-level instructions.
All right, I'd like to switch the topic. I want to mention the most upvoted question on the website here. One of the most practical concerns in AI research is getting data. Academia, we often struggle because we don't have much data. The companies are sitting on top of huge storehouses of data. But even in companies, if you actually look inside, you'll find that there's legal issues and privacy issues. It's not really so easy all the time for companies to use data. So do we need new means of handling, managing data? And what are the perspectives both from academic and industrial sides? So that's for anyone to take. this question.
So I have a contrarian take. So I would like somebody who actually believes that data is the big problem to talk first, and then I can say my thing.
The vision and language folks are the ones that use the most data, right? Vision, definitely.
Yeah, so I was actually going to say the opposite maybe, where I think some of the interesting problems are the ones where you're trying to do useful things where you don't have a lot of data, you don't have a lot of annotated data. And I do think those are the cutting edge problems. I think a lot of the work where you could just throw larger and larger models, add more and more data, that's kind of been done to quite an extent in the last few years. And I think the places where the interestingness lies is in this space where what can you do without that much data. And that also sets it up well for academic groups where if you don't have a lot of data, you don't have a lot of GPUs. I think there's a lot of interesting work to be done there. And so, yeah, that's one take.
I agree with what Debbie said, and that's an area that we're interested in with my group as well. But I mean, on the other hand, we like to, especially as academic researchers, emphasize the value of good ideas, but there is unfortunately no denying the fact that for what's happened in the last decade, the power of big compute and the power of big data has been producing at least as many advances as good ideas. I mean, for the last couple of years, we've sort of gone out of doing machine translation, but for a number of years when we were doing machine translation, I tried to, tote up at the end of the year how much our numbers have gone up and how many of them could be attributed to good ideas versus having scaled up the amount of training data that we had. And the sad fact was that normally the amount of training data won as being the single, maybe it's because it was counted as one factor, but it was sort of the single factor that produced the most improvements. So it is a real issue for people working in academia as well to sort of get data sets. But there have been positive developments. I mean, they're now, through efforts of both academics and companies, there are actually in a lot of areas quite good, large public data sets available.
And if I can just add to that a little bit, I think even with open research, I think there can be good back and forth, where if someone does train a large model with a lot of data, but if they're able to open source it and put it out there, where others don't have to replicate it, but they can start with something that's pre-trained, I think that helps a little bit with this as well.
I think one of the issues with the data is that it's not just data, it's actually labeled data and aligned data and kind of it's expensive data, right? That you have humans that have to kind of go through it. And, so that's why I think there's a lot of interest in current AI research about, unsupervised and self-supervised methods, which would in some sense level the playing field, where you could just turn on cameras and just collect data and then try to learn from that directly rather than having supervised learning kinds of data sets that are currently being used.
So I wanted to actually just bring up this other aspect of it that, I keep thinking of this idea called Polanyi's revenge. AI currently has been equated with dealing with tacit knowledge tasks that we didn't know how to do. We didn't know how we see the world. We don't know how we actually understand language. It's amazing progress has happened there. To some extent, there's some connection with that with system one, but we're also shifting completely into even cases where humans have models because of the civilizational knowledge. We would like to act as if, let's just convert it all into data and try to learn our own representations. And like somebody who's interested in interpretability, I just shake my head at that, because why would you go out of your way to ignore shared models when they're actually explicit knowledge available? So I think all these issues about what to do with data for tacit knowledge tasks like, robot manipulation or vision or language, I completely agree. But there are many, many things, like the way Samsung runs various of its divisions, for example. I'm pretty sure you guys are not just doing simulation and figuring out what you have some reasonable doctrine. And we should be actually trying to combine doctrine, explicit knowledge with learned representations. And that's something that I would love to see And I just wanted to bring that up because people coming into AI right now just think AI meant classically vision and language. And, we're all old here, especially Chris, probably, as still I'm the oldest probably. There was a time when basically language people were thought, this is not working anywhere. AI is not that. AI is the stuff that has like explicit knowledge model based. And, we were wrong then, we are wrong now. We need to combine explicit and tacit knowledge. That's what human intelligence is all about. I actually put up this thing on my Twitter page. I gave this talk last week on Polanyi's revenge and how that affects, AI's, progress. And we should think about that. I mean, if I'm working on tacit knowledge tasks, this is very important to figure out how to get label knowledge, etc. But then I shouldn't expect, interpretability to come easy at all.
I think this is a perfect segue to the final question. All right, so the title of today's session has been Human-Centered AI, and the reason is that, as people have alluded to on the question boards, the applications of AI today are for companies mainly to improve existing products and services. And a lot of application of AI is really human in the loop because AI can't do the whole thing by itself, right? And so, people are thinking to the future. When are we going to see people in the questions in the Q&A board? They say, when are we going to see real human-like AI? AI that can really equal human intelligence. And so here's the big question. It's taken us maybe 60, 70 years to get from the dawn of AI to where we are now. Will AI equal human intelligence? I assume everyone thinks it will happen. You're all AI boosters, so you all think it's going to happen eventually, probably. But will it happen in more than 70 years or less than 70 years? And why do you think that? Is what remains harder or easier than what happened before?
Probably negative. I think we've had some amazing progress by, throwing data and compute and big machine learning models. I mean, we should recognize it's so stunning what's been achieved in the last decade. I mean, AI has just moved so far in the last decade compared to what happened in the 3 decades before that, I think it's fair to say. But, I think we are, reaching the limits of the range of problems that you can solve by just throwing lots of data at big machine learning models, the kinds that we currently have. And I think we'll sort of increasingly start to realize how hard are the problems that we don't yet know how to solve. So, 70 years is a long time away, so it's hard to tell that far. But, I definitely don't think it's 20 years, and I'm not sure it won't prove to be that, it'll be more than 70 years.
The singularity. Go ahead.
Yeah, I was going to say, I think I agree. I think what remains is much, much harder than what we've done so far. I mean, even the things that we consider quote unquote solved with large quantities of data, if there is like just an interactive system and you interact with it for like 5 minutes, you're going to run into things that just break, right? So it's not, I think there's definitely much more left than what we've gotten done.
So, I mean, if you take something like GPT-3, which is quite amazing in terms of what it can produce as text, right? It basically suffers from all sorts of things in the form of our system 2 abilities. It's not that we don't think racist and sexist thoughts. Maybe some of you are much nicer than me, but we know how to filter them. We know how to get along in a civilization. And I think that part we have not at all figured out yet. Essentially, we haven't basically, trying to learn this just as I will learn everything by looking at the behavior of people over gazillion computational generations and then try to be human. That seems like too long a thing. My way in which your customers can get human-like abilities is we combine what we know about how to do tasks with the representations that we learn for vision and language and manipulation. And that used to be the normal way to do things, but that's kind of become quite the sort of the black sheep of the AI family right now. And I think it's, the end-to-end, when I think it came up in Daniel's talk, end-to-end, I just sort of rolled my eyes up. End-to-end, starting from now, let's just, speed up evolution until we get to the humans. That's what Jeff Hinton would say, that if the AI systems somehow develop in such a way, the way we develop, then they can talk to us. I think that's too long. Don't want to wait for that rapture. I want to have working systems that I can interpret way before that. And I think that we should be considering that aspect. As to exactly when human level AI would be reached, I think that's a sort of a tricky question. I don't even know that it's well defined, honestly.
All right, Dan, you have the last word now.
Well, in robotics, I would say that AI hasn't made as much of an impact as, say, in the vision and language communities. I'm involved in an effort, where we try to play robot soccer, and the goal there was to create a team of robots that could beat the world's best human soccer team. And we just I think we're pushing the deadline further and further in the future into when that will happen. But I agree with Chris, 7 years is a very long time, so it's really hard to make predictions on that time scale. But I'm optimistic, but I think there are lots of hard problems and this is why we need smart people to work on these problems, and this is why we need, academics and companies doing research in this area.
Is there time for me to make one more comment?
Okay, but after that, I'm going to be kicked off the stage. They're telling me to go. So please.
Okay. Another thing that you'd mentioned, Sebastian, was at the moment that AI is mainly the tool of the huge tech companies using it to optimize their systems. I think, before we have artificial general intelligence, a huge area where we could have a lot more emphasis is producing AI systems that actually work for regular people, not for the huge corporations. This is kind of the same as you want your own lawyer not to be represented, not only for the company to have a lawyer, right? And I think that's actually a big area that should be being pursued. And given how the world is heading at the moment, really the most likely avenue is for your mobile phone to hold the AI that will represent you.
All right, that's a positive spin on on-device AI. Let's hope it works out. Well, thank you so much. I mean, this has been a really fun discussion. I really hate the fact that we have to cut it off. But maybe next year we can do it in person. The talks were really incredible. So I learned a lot. So thank you very much. So the sessions for the AI Forum are finished. All the sessions will be uploaded at the Samsung YouTube channel right after the forum. So you can feel free to replay these sessions. You can tell your friends to watch these great lectures. This material has been translated also into Korean, so to make it accessible to people here in Korea. So this is going to be a really great resource, and I thank our experts. I think it's been a very meaningful time for us. We discovered very interesting perspectives about AI itself, but also how AI fits into our larger world. And of course, we all want to have a positive impact on the world, and we're trying our best to achieve that. So thank you very much, and I look forward to seeing you in 2021. And let's hope that all goes well and we can do this in person. I got my fingers crossed. And so thank you very much for joining us. And good day or good night, depending on where you are. Bye all.
Okay, thank you very much for the wonderful discussion. Also, our present led this discussions very wonderfully. As you mentioned, once again, we really appreciate your participation at the end of the conference, and we hope to meet you offline next year. Thank you very much.